Now we are going to discuss another concept, which is the simplifications. So we are going to see what are we are learned regarding the trigonometric Fourier series and the exponential Fourier series. So now we are going to do some simplifications that we are going to see here. So listen carefully. That f of t is equal to a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus by n sin n omega naught t. So this a representation of the trigonometric Fourier series for a periodic signal which is having the time period of t. So omega naught is equal to pi by t. Suppose the signal f of t is a real signal with even symmetry, then what is going to happen? Suppose if the periodic signal is a real signal and with even symmetry, then what is going to happen? That we are going to see. Even symmetry means it is an even signal. It is symmetric with respect to y-axis. Then I have already told you if a signal is said to be even symmetry or even signal, then we can say f of minus t is equal to f of t. So f of minus t is equal to f of t. Then we say it is a even signal or the even symmetry. Then what is going to happen? That we are going to see. See, I have already told you a naught is nothing but 1 by t integration over the t f of t dt. As f of t is an even signal, so definitely we can say a naught is, we are going to get some finite value. So we can say it is not equal to 0 generally. Similarly, a n is nothing but 2 by t integration over the t f of t cos n omega naught t dt. Here f of t is an even signal and cos is also even signal. So multiplication of two even signals, we are going to get again even signal. So if you are going to do the integration over the one time period, so for even signal, again you are going to get some finite value. So this is also not equal to 0 generally. Now let's go for the Bn. So Bn is equal to 2 by t integration over the t f of t sin n omega naught t dt. As f of t is even signal and sin is the odd signal. So multiplication of even signal and odd signal is odd signal. So for odd signal, if you do the integration over one complete time period, so then it is going to give you 0. So therefore Bn is equal to 0 always. So Bn is equal to 0 always means we can say for the f of t real signal with even signal, or we can say f of t is basically even signal. We can say real signal means there is no complex term. That's it. There is no complex term in that signal. Then we can say as f of t is even symmetric signal or the even signal, we can say a naught is not equal to 0 generally and a n is also not equal to 0 generally, but Bn is equal to 0 always. Then what the terms that you are going to get? So a naught you are going to get, a n you are going to get. So Bn is absent. So therefore for this signal there will be DC term as well as the cos terms. Only these things are going to get present. Then what is Cn? Cn is nothing but I have already told you Cn is equal to n by 2 minus j Bn by 2. See, as Bn is equal to 0, so Cn is always real. So as Bn is equal to 0, so there is no complex term. So Cn is purely real. So Cn is purely real means we can say Cn is nothing but in the case of exponential Fourier series, this is a Fourier series coefficient Cn. So Cn is purely real in that case. So purely real in that case. So now let's go for the other thing. Suppose if f of t is a real signal with odd symmetry, real signal means there is no complex term j and it is an odd symmetry means it is an odd signal. Then I have already told you for an odd signal f of minus t is equal to minus of f of t. So f of minus t is equal to minus of f of t, or you can write vice versa also. F of t is equal to minus of f of minus t means we can say that is anti-symmetric with respect to y-axis. So now what is going to happen for the Fourier series coefficients that we are going to see in the trigonometric as well as the exponential. So a naught is equal to 1 by t integration over the t f of t dt. As f of t is an odd signal, so integration over the one complete cycle we are going to get 0. So this value is equal to 0 always. And a n is nothing but 2 by t integration over the t f of t cos n omega naught t dt. As f of t is a odd signal and cos is a even signal, so multiplication of odd and even is nothing but odd. So integration over the one complete time period for odd signal is nothing but we are going to get its value is equal to 0. So n is equal to 0 always. Then Bn. So Bn is nothing but 2 by t integration over the t f of t sin n omega naught t dt. As f of t is a odd signal and sin is also odd signal, so multiplication of two odd signals we are going to get the even signal. So integration over the one complete time period for even signal, you are going to get some non-zero value. So therefore we can say Bn is not equal to 0 in this case. Then a naught is 0, an is 0 and Bn is not equal to 0 in the case of this signal. So we can say the DC term is absent, all the cos terms are absent, but all the sin terms are present. Now let's see for the the Cn coefficient. So Cn is nothing but an by 2 minus j bn by 2, as a naught is equal to 0 and an is equal to 0. So if an is equal to 0 means only the complex terms are going to get present. So it's a purely imaginary. It's a purely imaginary. If a naught is equal to 0, then c naught is also equal to 0. So we can say in the case of exponential Fourier series, in the exponential Fourier series, there is no DC term. Only there will be the Cn will be purely imaginary nature. So therefore we can say that in the case of trigonometric Fourier series, DC term is absent, cos terms are absent, only sin terms are present. In the case of exponential Fourier series, the Cn is always purely imaginary. It is always purely imaginary. Now let's go for the another thing, which is basically we can say, suppose if f of t is a real signal with half wave symmetry. So here f of t is basically a real signal with half wave symmetry. Then what is going to happen? Let's see. So what is the meaning of half wave symmetry means? So this is the condition. So f of t is equal to minus of f of t plus or minus t by 2. So this is called as the half wave symmetry. So f of t is equal to minus of f of t plus or minus t by 2. Suppose there is some signal. That signal just give a delay by t by 2. Just give a delay by t by 2 and flip it and reverse it. And you should get the same signal. So if you want the example means, I will go for this one. So I will go for this one. So let me give a small example so that we can easily able to understand. So I will give a signal like this. So this is a signal I will try to give. So I will give a signal like this, periodic signal. So this is the t by 2 and this is the t. So it's a periodic signal in this fashion for all the time. So it's a periodic signal, right? Here also periodic signal. Suppose now if I give the delay by t by 2, so then this will come here. So this will come here. And this will come here, right? So now do the negative of the term. So you are going to get the original signal, right? So therefore this is called as the half wave symmetry signal. So half wave symmetry signal is nothing but f of t is equal to minus of f of t plus or minus t by 2 means give the delay or advance. Either delay or advance you can give. For a given signal f of t, either you give the delay the signal or advance the signal by t by 2 and just flip the signal, you should get the original signal. Then only we can say that is called as the half wave symmetry. So f of t is equal to minus of f of t plus or minus t by 2. So therefore we can say f of t is equal to minus of f of t plus or minus t by 2 means for the given signal f of t, just delay or advance by t by 2 and flip that signal, means reverse that signal. And then reverse means positive will become negative, negative will become positive. Then you should get back the original signal. If that is the case, then we can say it is a half wave symmetry signal. So this is the example I have shown here. So if f of t is equal to minus of f of t plus or minus t by 2, then we can say it is a half wave symmetric signal. Then what is going to happen? Let's see here. So now listen carefully. What is going to happen? Let's see here. Cn is equal to 0 for n is equal to 0, 2, 4 and goes on. So for all the even values of Cn, its value is equal to 0. For all the even value of Cn means, we can say exponential Fourier series coefficient Cn for all the even values of n, its value is equal to 0. And if Cn is equal to 0 means Cn is nothing but an minus n by 2 minus j bn by 2. As Cn is equal to 0, by comparing the real part and imaginary part, we can say n is also equal to 0 and bn is also equal to 0. For the even values of n, which is 0, 2, 4 and goes on. So n is equal to 0 and bn is also equal to 0. For n is equal to 0, 2, 4 and goes on. And C naught is nothing but it is a theory. We can say n is equal to 0 if you substitute. C naught is also equal to 0. So therefore C naught is nothing but A naught. So its value is also equal to 0. So from this what we can say, A naught is equal to 0 and An is not equal to 0 for n is equal to odd and Bn is not equal to 0 for n is equal to odd. So then what is going to happen? All the in the case of trigonometric Fourier series, the DC term is absent and all the odd harmonic cos terms are going to be present and all the odd harmonic sin terms are going to be present. So therefore only odd harmonics of the sin and cos only are going to get present. So listen carefully what I am trying to tell you. In the case of half wave symmetric signal, which is f of t is equal to minus of f of t plus or minus t by 2, we can say Cn is equal to 0 for all the even values of n, which is n is equal to 0, 2, 4, like that. So 0, 2, 4 and like that it will go for all the even values of n. So Cn is equal to 0 for even values of n, which is n is equal to 0, 2, 4 and goes on. So the value of Cn is nothing but an by 2 minus j bn by 2. So by comparing the real part and imaginary part, we can say n is equal to 0, bn is equal to 0 for even values of n, which is n is equal to 0, 2, 4 and goes on. So what if we substitute here n is equal to 0 in place of Cn, then C0 is equal to 0, C0 is nothing but A0, so A0 is also equal to 0. So therefore, we can say finally A0 is equal to 0 and An is not equal to 0 for all the odd values of n, and Bn is not equal to 0 for all the all the odd values of n. So therefore, we can say finally, in the case of trigonometric Fourier series, we can say the digit term is absent and only cos terms and sine terms of odd harmonics are going to get present. Only odd harmonics of sine and cos terms are going to only present. So this is what I am trying to tell you. So finally, I can say, suppose if a signal is said to be half-wave symmetric, means f of t is equal to minus of f of t plus or minus t by 2, means just delay or advance the signal by t by 2, and negative means minus will become plus, plus will become minus, and if you match the f of t, it should be equal. Then only we can say it's a half-wave symmetry. For the case of half-wave symmetric signal, Cn is equal to 0 for all the even values of n, which is n is equal to 0, 2, 4 and goes on. Cn is nothing but an by 2 minus j bn by 2. As we are going to equal the real part and the imaginary part to 0, an is equal to 0 and bn is equal to 0 for all the even values of n, which is 0, 2, 4 and goes on. 0, 2, 4 and goes on. See, as in place of n, you substitute 0. In place of n, you substitute 0. C0 is equal to 0. C0 is nothing but A0. So A0 is also equal to 0. So therefore, finally I can say A0 is equal to 0 and An is not equal to 0 for all the odd values of n, and Bn is not equal to 0 for all the odd values of n. So we can say finally in the case of trigonometric Fourier series, and this term is absent, and all the odd harmonics of sine and all the odd harmonics of cos, only these terms are going to get present in the trigonometric Fourier series for this type of half-wave symmetric signal. Now let's go for the other signal, which is f of t is a real signal with even nature as well as the half-wave symmetry. So basically here the signal is even signal as well as half-wave symmetric signal also. These two properties are going to get satisfied. So if a signal is going to satisfy the two properties, one is the even nature and the half-wave symmetry. So whatever the three things that we have done, right? Up to now what we have done, the basic concepts of the odd signal, the basic concepts of the even signal, and the basic concepts of the half-wave symmetry. So now we need to club the two things. What is the even nature and the half-wave symmetry? That's it. So the even signal means I already told you f of minus t is equal to f of t. And what is half-wave symmetry? I already told you f of t is equal to minus of f of t plus or minus t by 2. So this is for the even nature and this is for the half-wave symmetry. So the signal is going to satisfy these two properties. It is an even signal as well as the half-wave symmetric signal. So now we need to club these two properties. So therefore we can say in the case of even so now we can say clearly. See, we know. So in the case of even signal, what I have told you, in the case of even signal, I have already told you, A0 is not equal to 0 and An is not equal to 0, but Bn is equal to 0. I have already told you, right? So listen carefully. So in the case of even signal, what I have told you, in the case of, let me write here. In the case of even signal, what I have told you, so let me write here. Let me write in other paper. So I have already told you, in the case of even signal, what I have told you, in the case of even signal, I have already told you, A0 is not equal to 0 and An is not equal to 0, but Bn is equal to 0 always. So this is what I have told you for the even nature. And for the half-wave symmetry. For half-wave symmetry, what are the conditions? I have already told you. Just now we have discussed A0 is equal to 0 always, and An is not equal to 0 for n is equal to odd. And Bn is not equal to 0 for n is equal to odd. Just now we have discussed, right? So just now we have discussed. Now we need to combine these two things. So we need to combine these two things because the signal is going to satisfy the two properties, even nature as well as the half-wave symmetry. From this, what we can say here, A0 is not equal to 0, but here in this case, A0 is equal to 0. So finally, we can say a0 is equal to 0 because it is became 0. Here n is not equal to 0. Here n is not equal to 0 for n is equal to r. So definitely what we can say that n is not equal to 0 for n is equal to r. So we can say n is not equal to 0 for here all values of n, in all values of n, but here only for odd values of n. So therefore you have to come this part only for odd values of n. So only for the odd values of n. Now then bn, here bn is equal to 0 always, here bn is not equal to 0 always, means here bn is not equal to 0 for n is equal to r, means definitely it will become for always, it will become always null. So bn is equal to 0 always. So this is what we can say. So this is the thing finally. A0 is equal to 0. See, if 1 is not 0, other is 0 means by default is 0. That's it. Here 1 is not 0 and other is 0 means by default will become 0. See, here 1 is not 0 and other is 0 means by default will become 0. Here 1 is 0 and other is not 0 means by default will become 0. Here for all the values of n it is not equal to 0. But here only for odd values of n it is not equal to 0. So we have to take here only for odd values of n it is not equal to 0. Or we can also write like this. Or what we can write second case. Or we can write n is equal to 0 for n is equal to even. For n is equal to even. You can write like this or either you can write like this. So this is what I am trying to tell you. So finally a0 is equal to 0. an is equal to 0 for n is equal to even, or n is not equal to 0 for n is equal to odd, and bn is equal to 0 always. Then what is the thing that we are going to get? So in the case of trigonometric Fourier series, the basic term is absent, and also the all the sine terms are also absent. But now only odd harmonics of the cos terms are going to get present. Only the odd harmonics of the cos terms are going to get present. See, you can see here. So same thing. A0 is equal to 0 always, and all you have to do. And n is equal to 0 for n is equal to even, or n is not equal to 0 or for n is equal to odd. We can write it anything, right? I've already told you n is equal to 0 for n is equal to even, or we can also say, or we can say that n is not equal to 0 for n is equal to odd. We can write like this also. So n is not equal to 0 for n is equal to odd means n is equal to 0 for n is equal to even. So therefore bn is equal to 0 always. I've already told you. So therefore the basic term is absent and all the sine terms are absent. Only the odd harmonics of sine cos terms are going to get present. So only odd harmonics of the cos terms are going to get present for this signal. So now let's go for the other property, which is if f of t is a real signal with odd nature and the half wave symmetry. So now they are saying that the signal is going to satisfy the two properties. One is the odd signal property and also it is a half wave symmetry. I have already told you odd nature means odd signal means we can say f of minus t is equal to minus of f of t. This is called as odd signal. And half wave symmetry means I have already told you f of t is equal to minus of f of t plus or minus t by 2. So the signal is going to satisfy the two properties. So from this we have to tell what are the conditions are going to happen. Let's see. Same thing. Here also we are going to see the analysis. So same thing, same analysis we are going to do. So this is for the odd and this is for the half wave symmetry. So in the case of odd, I have already told you a0 is equal to 0 and an is equal to 0 and bn is not equal to 0. So this is what I have told you in the case of odd. In the case of half wave symmetry, just now we have discussed a0 is equal to 0 and an is not equal to 0 or n is equal to odd. Right? And bn is not equal to 0 or n is equal to odd. Just now we have discussed for the half wave symmetry. So now we need to club these two properties because the signal is going to satisfy these two properties. So from this we have to say what is the overall parameters of the for the series coefficients are there. So we can say here a0 is equal to 0 and here also a0 is equal to 0. So finally here it will be a0 is equal to 0 only. So it will be a0 is equal to 0 always in this case. So in this case then here an is equal to 0 and here an is not equal to 0. So you can see here n is equal to 0 and here an is not equal to 0. Here n is equal to 0 for all. Here n is not equal to 0 for only n is equal to 1. So it is 0 for all means definitely it will become 0 for all things. So definitely it will become an is equal to 0 always. So an is equal to 0 always. So always. So always. Now here bn is not equal to 0 for all values of n and Vn is not equal to 0 for only odd values of n. So definitely it will become this one only. So therefore Vn is not equal to 0, is not equal to 0 for all for values of odd, or you can say like this also, or you can say vice versa. Vn is equal to 0 for even values of n, for even values of n. You can say like this also, we can say. You can say like this. So therefore we can say by clubbing the two properties, we are going to get the overall properties here. For the odd, a0 is equal to 0, an is equal to 0, and Vn is not equal to 0. For half-wave symmetry, a0 is equal to 0, and an is not equal to 0 for n is equal to odd, and Vn is not equal to 0 for n is equal to odd. So by clubbing these two properties, we can say here a0 is 0, here also a0 is 0. So finally, a0 will be 0. Here n is equal to 0 for all values of n. Here n is not equal to 0 for only odd values of n. So if we combine this, definitely we are going to get this one, which is n is equal to 0 for all values of n. And here Vn is not equal to 0 for all values of n. But here Vn is not equal to 0 for only odd values of n. So if we club these two things, we can say Vn is not equal to 0 for only odd values of n, or you can say Vn is equal to 0 for even values of n. So from this what we can say that this term is absent and all the cos terms are also absent. Only the odd sine terms, odd elements of sine terms are going to get present. So you can see clearly here. So we can say a0 is equal to 0, I already told you, always, and an is equal to 0, always. Vn is equal to 0 for even values of n, or we can say, or we can also say Vn is not equal to 0 for odd values of n. So we can say Vn is not equal to 0 for only odd values of n. So therefore we can say that only odd values of sine terms are going to get present. So this is what I have told you. Now let's go for the another thing. Suppose if f of t is a real signal with no symmetry. No symmetry means there is nothing like anything. See, the odd, we can say the odd signal property is not satisfied, the even signal property is not satisfied, and half-wave symmetry is also not satisfied. So suppose I have taken some signal and I have checked all the properties of the odd nature, even nature, and the half-wave symmetry. All these are not satisfied. All these are not satisfied. So we can say it is not having any symmetry. So suppose some periodic signal they have given. So I have checked the odd property, I have checked the even property, and I also checked the half-wave symmetry property. All these properties are not satisfied. So we can say the signal is not having any symmetry. So from this we can say a0 is not equal to 0 generally, and an is also not equal to 0 generally, and Vn is also not equal to 0 generally, because it is not having any symmetry. So then what is Cn? Cn we know an by 2 minus j Vn by 2. As n is not equal to 0 and Vn is not equal to 0, so Cn is a complex term. So therefore we can say in the case of any signal, it is not satisfying the odd nature, even nature, and half-wave symmetry. So finally we can say the signal will have the implicit term, all the cos terms, and all the sine terms, like trigonometric Fourier series, or Cn will be always in complex in nature in the case of the exponential Fourier series. So these points always you have to keep in your mind. So now, suppose f of t is the real signal with half-wave symmetry. Suppose if it is going to satisfy another property. So what is the property? Which is f of t is the real signal with half-wave symmetry. Here, now the half-wave symmetry is f of t is equal to plus f of t plus or minus t by 2. In the previous case, which is minus. So here it is a plus. So these things always you have to keep in mind. So this is a thing always you have to keep in mind. So therefore here f of t is equal to plus here, plus. Whereas in the previous case, which is minus. So this is the point always you have to keep in mind. So here f of t is equal to f of t plus or minus t by 2. So this is called as another half-wave symmetry. So this is another half-wave symmetry. So that is also half-wave symmetry, and this is also half-wave symmetry. But the conditions are different. So this point always you have to keep in mind. So this point always you have to keep in mind. So that is also half-wave symmetry, and this is also half-wave symmetry, but the conditions are different. It will be reverse of that one. It will be the reverse of that one. So this things always you have to keep in mind. So in that case, what you have studied? In that case, what we have studied? In that case, we have studied that very simple. There, Cn is equal to 0 for even values of n, but here Cn will be 0 for odd values of n. Reverse of that one. So we can say, suppose some signal is the f of t. Just say that you do the delay or advance by t by 2, and you don't have to flip. That signal is the same as the original signal. Then this is one more of a symmetry. Then what is going to happen? Then here Cn is equal to 0 for all the odd values of n, which is n is equal to 1, 3, 5, and goes on, only for odd values of n. So if you remember this one, then this is a quite opposite of this one. Here it is for even values of n, the Cn is 0. But here for odd values of n, the Cn is equal to 0. So this is a important thing always you have to keep in your mind. So I want you to remember only three important things. R signal property, even signal property, and half-wave symmetry. That half-wave symmetry is f of t is equal to minus of f of t plus or minus t by 2. If you remember these three things, then you can get any other signal properties also you can get. And this is also half-wave symmetry, but here there is no negative. F of t is equal to plus f of t plus or minus t by 2. Then in that case, what is going to happen? That we are going to only see. So this properties will be quite opposite to the half-wave symmetry that we have studied. There Cn is equal to 0 for all the even values of n, but here Cn is equal to 0 for all odd values of n, which is n is equal to 1, 3, 5, and so on. All the odd values of n. So Cn, an by 2 minus j bn by 2 is equal to 0 for all odd values of n. So by comparing the real part and imaginary part, we can say n is equal to 0 and bn is equal to 0 for all the odd values of n. N is equal to 1, 3, and 5, and so on. Suppose if you see C0 is nothing but only for n is equal to 1 onwards it is going to go. So then C0 is nothing but it is a even value of n for n is equal to 0, and its value is not equal to 0. So n is also not equal to 0 because C0 is equal to n0. C0 is nothing but here I have substituted n is equal to 0, n is equal to 0 is an odd value. So definitely its value is not equal to n is an even value, so its value is not equal to 0. So n0 is also not equal to 0 generally. So n0 is not equal to 0 generally. Then here an is equal to 0 for all the odd values of n. So an is not so an is not equal to 0. So we can say here an is equal to 0 for odd values of n. So definitely an is not equal to 0. It is equal to 0 for odd values of n. So therefore it is not equal to 0 for even values of n. So n is not equal to 0 for even values of n. And we can say the bn. So bn is nothing but. So bn is equal to 0 for all the odd values of n. So here it will be reverse. So bn is not equal to 0 for even values of n. It is just the reverse of that one. So therefore we can say that from this what we can say finally the DC term is present, and so the DC term is also present, and also here only the even cos terms are going to get present, and even sin terms are going to get present. Even arguments of sin and cos terms are going to get present, and the DC term is also going to get present. So only even arguments of sin and cos terms, the DC term is also going to get present. So with the DC term, so let me write here only even arguments of sin and cos and DC term are present. Let me have this only are present. So this is what I am trying to tell you. So we can say, let me have this part also. Even harmonics of sin and cos as well as a DC term are going to get present. So finally, what I can say, very simple. So finally, I will give you some important things. If you remember these things, then everything is simple. If you remember these things, then everything is simple. So listen carefully. For odd signal, I am going to write the properties. For odd signal, A0 is equal to 0, and AN is equal to 0, and BN is not equal to 0. So this is for all values of N. So now, for even signal, ES means even signal. For even signal, A0 is not equal to 0, and AN is not equal to 0, and BN is equal to 0. Now, let's go for the half-wave symmetry signal. Half-wave symmetry means the condition is here. F of t is equal to minus of f of t plus or minus t by 3. So t by 3. So this is the point here you have to remember. So here our signal is f of minus t is equal to f of minus of f of t. F of minus t is equal to minus of f of t. Everything minus. Here signal means f of minus t is equal to f of t. So for half-wave symmetry, so this is the half-wave symmetry. The condition is f of t is equal to minus of f of t plus or minus t by 2. Then we can say that here for this signal it will be A0 is equal to 0, and AN is not equal to 0 for n is equal to odd. So n is equal to odd, and BN is not equal to 0 only for n is equal to odd. So for this one, for another half-wave symmetry, what is doing this is another half-wave symmetry. Let me write here another half-wave symmetry. The condition is that f of t is equal to f of t plus or minus t by t. If it is satisfying this property, then what are the conditions? What are the conditions? Just now we have discussed. If it is going to satisfy this property, then what is actually which is going to happen is a quite reverse of that one. So there n is equal to 0. There it will be n is not equal to 0. Reverse. And here n is not equal to 0 for n is equal to 1. Then it will be even. So n is not equal to 0 for n is equal to even. And say n is not equal to 0 for n is equal to even. And there bn is not equal to 0 for n is equal to 1. So here bn is not equal to 0 for n is equal to even. That's it. So bn is not equal to 0 for n is equal to even. So this is what I'm trying to tell you. So I want you to remember all these things. So if you remember these things, then we can easily, these are 4 things always you have to keep in your mind. So these 4 signal properties always you have to keep in your mind. So these 4 signals always you have to keep in your mind. So therefore, then you can, for any signal, you can easily figure out what is a simplified Fourier series coefficients, you can easily simplify. So listen carefully. For odd signal means I have already told you f of minus t is equal to minus of f of t. Then a0 is equal to 0 and n is equal to 0 for all values of n and bn is not equal to 0 for all values of n. For even signal means f of minus t is equal to f of t, then a0 is not equal to 0 and n is not equal to 0 for all values of n and bn is equal to 0 for all values of n. Half-wave symmetry means f of t is equal to minus of f of t plus or minus t by 2. If this is a condition is going to get satisfied, then we can say this is one of the half-wave symmetry. Then a0 is nothing but it is always equal to 0 and an is not equal to 0 for n is equal to odd and bn is not equal to 0 for n is equal to odd. So what is the meaning of this one? An is equal to 0 for even values of n and bn is equal to 0 for even values of n. So this is what I am trying to tell you. So if you remember these 3 things, you have half-wave symmetry for the other signal which is f of t is equal to plus of f of t plus or minus t by 2 is reverse of this one. Here a0 is equal to 0, it will become not equal to 0. Here n is not equal to 0 for n is equal to odd means n will be not equal to 0 now for n is equal to even. And bn is not equal to 0 for n is equal to odd means it will become bn is not equal to 0 for n is equal to even. So if you remember these things, then you can get this one very easily. So I want you to remember all these things so that things are going to get simplified. So I want you to remember only these 3 things. If you remember these 3 things, with the help of this you can get this one also. You can get this one properties also you can easily get. So these things always you have to keep in the mind. So, see, this is what I am trying to tell you. So, these things always you have to keep in your mind. Here, let me give you some more idea here. Basically, this is called as a odd half-wave symmetry and this is called as a even half-wave symmetry. See, if I am telling you both these are half-wave symmetry, you will get confused. So, that is the reason I am calling this as the odd half-wave symmetry and this is the even half-wave symmetry because in this case, only the odd sine and cos terms are going to get present. And here, only the even and the even sine and cos terms are going to get present. So that is the reason this is called as even half-wave symmetry and this is the odd half-wave symmetry. So therefore, in the case of odd half-wave symmetry, f of t is equal to minus of f of t plus or minus t by 2. So therefore, a0 is equal to 0 and an is not equal to 0 for n is equal to odd and bn is not equal to 0 for n is equal to odd. So that is the reason here only the odd harmonics of the sine and cos terms are going to get present. So that is the reason it is called as the odd half-wave symmetry. And this is f of t is equal to plus f of t plus or minus t by 2. So that is the reason it is called as the even half-wave symmetry. And here a0 is not equal to 0 and an is not equal to a0 is not equal to 0 and an is not equal to 0 for n is equal to even and bn is not equal to 0 for n is equal to even means for the even harmonics of sine and cos terms are going to get present. So that is the reason it is called as the even half-wave symmetry. So odd half-wave symmetry means only the odd harmonics of the odd harmonics of sine and cos terms are going to get present. Even half-wave symmetry means only the even harmonics of the sine and cos terms are going to get present. So this is what I am trying to tell you. So see, instead of telling both are half-wave symmetry means you will get confused. So this is the actual notation. Just now I got to remember. So this is called as odd half-wave symmetry and this is called as the even half-wave symmetry. So in the case of odd half-wave symmetry, only the odd harmonics of sine and cos terms are going to get present In the case of even half-wave symmetry, the even harmonics of sine and cos terms are going to get present. So if you remember like this, then everything is very simple. So this is what I'm trying to tell you. Suppose if you give any signal, if it is going to satisfy any two conditions, with the help of those two, clubbing of those two properties, we can get the overall conditions, right? Suppose the signal is going to satisfy the R symmetry as well as the odd half-wave symmetry. If these two conditions are satisfied, means with the clubbing of these two things, we can get the overall properties. Suppose if the signal is going to satisfy the original property as well as the even half-wave symmetry, then by clubbing these two properties, we can get the overall properties. Similarly, if a signal is going to satisfy the even symmetry as well as the odd half-wave symmetry, then with the help of these two conditions, we can get the overall conditions. Suppose if a signal is going to satisfy the even symmetry as well as the even half-wave symmetry, then with the help of these two conditions, we can get the overall parameters. So this is what I am trying to tell you. So this is the odd half-wave symmetry and this is the even half-wave symmetry. So here positive means even half-wave symmetry. Here negative means odd half-wave symmetry. So shortcut to remember. So here positive means even half-wave symmetry. Here negative means odd half-wave symmetry. Odd means all the odd elements of sine and cos terms are going to get present. Even means all the even elements of sine and cos terms are going to get present. So that is the reason always you have to keep in your mind. So now let's go for the some important properties of the Fourier series coefficients. So now we are going to discuss the properties of the Fourier series coefficients. So we are going to discuss the properties of the Fourier series coefficients. So basically, the exponential Fourier series coefficients Cn only we are going to discuss. Only the Cn we are going to discuss. Only the exponential Fourier series coefficient Cn we are going to discuss in very detailed manner. So here, suppose for f of t, the exponential Fourier series coefficient is Cn. So for f of t, the exponential Fourier series coefficient is Cn. Suppose for f of t plus t naught, then what is the exponential Fourier series coefficient is Cn into e to the power of j n omega naught t naught. So for f of t plus t naught, the Fourier series coefficient will be Cn into e to the power of j n omega naught t naught. J n omega naught t naught. And for f of t minus t naught, the Fourier series coefficient is Cn into e to the power of minus j n omega naught t naught. So this is the point always you have to keep in your mind. Here positive means here also positive. Here negative means here also negative. So in simple ways I can write like this. So in simple ways I can write. So in simple ways what I can write, the simple ways is for f of t plus or minus t naught. What is the Fourier series coefficients? Cn into e to the power of plus means plus, minus means minus. So Jn omega naught t naught. So this is what in simple words I can say. F of t plus or minus t naught is something that Cn into e to the power of plus or minus Jn omega naught t naught. Here positive means here positive, here negative means here negative. So this is the point always you have to keep in mind. So for f of t, if the Fourier series coefficient is Cn, then for f of t plus or minus t naught, the Fourier series coefficient is Cn into e to the power of plus or minus Jn omega naught t naught. So listen carefully. For f of t, the Fourier series coefficient is Cn, then f of t plus or minus t naught will have the Fourier series coefficient Cn into e to the power of plus or minus j n omega naught t naught. Now let's go for the another property. Suppose for f1 of t, the Fourier series coefficient is Cn1, and for f2 of t, the Fourier series coefficient is Cn2, and both are having the same time period. So both have same time period means f1 of t and f2 of t both are bloody signals and they have the same time period. Then if you do the addition of this one, which is a1 into f1 of t plus a2 into f2 of t, then the resultant Fourier series, then this is basically it is the resultant Fourier series we are going to get. If these two are periodic signals of same time period, then the overall signal is also periodic signal of the same time period. So it will have the Fourier series coefficient is a1 into Cn1 plus a2 into Cn2. So listen carefully. For f1 of t, the Fourier series coefficient is Cn1. For f2 of t, the Fourier series coefficient is Cn2. And both are having the same time period. Then a1 into f1 of t plus a2 into f2 of t will have the resultant Fourier series coefficient, which is a1 into Cn1 plus a2 into Cn2. So this is what we have to understand. So therefore, for f1 of t, the Fourier series coefficient is Cn1, and for f2 of t, the Fourier series coefficient is Cn2, then a1 into f1 of t plus a2 into f2 of t will have the resulting Fourier series coefficient, which is a1 into Cn1 plus a2 into Cn2. So this is the point always you have to keep in your mind. Then suppose if f of t has the Fourier series coefficient Cn, then d by dt of f of t has the Fourier series coefficient j into n into omega naught into Cn. And you can say the kth derivative of f of t, we have the forces coefficient j into n into omega naught whole to the power of k into Cn. So this would always you have to keep in your mind. So therefore we can say that, so for d by dt of f of t, we have the forces coefficient j into n into omega naught Cn, and d by dt and k derivative of f of t, we have the forces coefficient which is n into j into n into omega naught whole to the power of k into Cn. So these formulas you have to remember. So now for f of t, the forces coefficient is Cn, then a plus f of t, we will have the forces coefficient Cn for n not equal to 0, and for n is equal to 0, it is C naught plus n, because we are adding dc term, right? So if we are going to add the dc term, this dc term is going to add only for the dc Fourier series coefficient. So therefore we can say for the remaining things it will be Cn only, but only for dc term it will be a plus C naught. So a plus C naught. So this dc term we are going to add to f of t. So if we are going to add a dc term for f of t, that dc term is going to add to the dc term only, and the remaining things will be same as it is. So therefore we can say, and the remaining Fourier series coefficient will be same as the previous one. So therefore we can say that Cn is equal to, for Cn for n not equal to 0, and C naught plus a for n is equal to 0, means only the dc terms are going to get added, and the remaining thing will be same as it is. The Fourier series coefficients will never change. It will never change. Only the dc part is going to get changed, which is a plus C naught, whereas the remaining things will never change. So now for the next property, which is for f of t, the Fourier series coefficient is Cn. For f of t, the Fourier series coefficient is Cn, and for f of minus t, suppose if we take f of minus t which is equal to g of t, it will have the Fourier series coefficient as C of minus n. Suppose for g of t, the Fourier series coefficient is Bn, g of t is equal to f of minus t, so its Fourier series coefficient will be C of minus n. So B1 is nothing but C of minus 1, B2 is nothing but C of minus 2. So this is what I am trying to tell you. So for f of t, the Fourier series coefficient is Cn, so f of minus t will have the Fourier series coefficient C of minus n. If f of t is even, then definitely Cn is equal to C minus n. Suppose if f of t is odd, then Cn is equal to minus of C of minus n. So this is the thing always you have to keep in your mind. If f of t is even, then C of n is equal to C of minus n. If f of t is odd, then C of n is equal to minus of C of minus n. So for f of t, the Fourier coefficient is Cn for time period t1, and g of t is having the Fourier coefficient dn for time period t2. Then basically you can see f of t is having the Fourier coefficient Cn for time period t1, and g of t is having the Fourier coefficient dn for time period t2. So now we need to make these things on a common time period. So both are having a different time period, right? So now for on a given time period, on the same time period, now I need to figure out this Fourier series coefficient, which is f of t is having the Fourier series coefficient Cn dash for time period t, and g of t is having the Fourier series coefficient dn dash for time period t. So for the common time period, I need to figure out the Fourier series coefficient. Now we have to do the a1 into f1 of t plus a2 into g of t. Now it will have the resultant Fourier series coefficient, which is a1 into Cn dash plus a2 into dn dash, where the overall time period, the count time period is the LCM of the individual time periods. But the overall time period is the LCM of the individual time periods. So let me repeat this one again. I think I have gone very fast, but still let me repeat this one. Suppose for f of t, the Fourier series coefficient is Cn, then for f of t plus or minus t naught, the Fourier series coefficient is Cn into e to the power of plus or minus j n omega naught t naught. So listen carefully. For f of t, the Fourier series coefficient is Cn, and for f of t plus or minus t naught, the Fourier series coefficient is Cn into e to the power of plus or minus j n omega naught t naught. Suppose if f1 of t is a periodic signal which is having a time period t, which have a Fourier series coefficient of Cn1, and f2 of t is a periodic signal which is having a time period t, and it's having Fourier series coefficient Cn2. Suppose if I do the scalar multiple and the addition, which is we can say the linear combination of these two signals, which is a1 f1 of t plus a2 f2 of t. It is also as f1 of t is a periodic signal and f2 is also periodic signal of same time period. If we do a linear combination, still the resonant signal is also periodic signal of same time period. So it will have the Fourier series coefficient, which is a1 into Cn1 plus a2 into Cn2. So for f of t, if the Fourier series coefficient is Cn, then the first derivative of f of t has the Fourier series coefficient j into n into omega naught into Cn. And the kth derivative of f of t has the Fourier's coefficient j into n into omega naught all the power of k into Cn. And if f of t has the Fourier's coefficient Cn, then a plus f of t. A plus f of t is nothing but it's a new signal. So DC shift, either you are shifting the signal upward or downward with the help of A. Then this resultant signal will have the Fourier's coefficient Cn for n not equal to 0, and its value is equal to for n is equal to 0, its Fourier's coefficient is C naught plus A, because then the DC terms are going to get added and the remaining terms will be remain as it is. See, whenever you are going to add for f of t, basically you are shifting the signal either upward or downward. The Fourier's coefficient will remain as it is for n not equal to 0. Only at n is equal to 0, and the DC terms are going to get added, which is A naught plus C naught plus basically C naught plus A. And for f of t, the Fourier's coefficient is Cn, and f of minus t. F of minus t will have the Fourier's coefficient C of minus n. So f of minus t I am going to assume should have t. So C of minus n I am going to assume Bn. So therefore if substitute B1 is nothing but C of minus 1, B2 is nothing but C of minus 2, like that. If f of t is even, then Cn is equal to C of minus n. And if f of t is odd, then C of n is equal to minus of C of minus n. And I have already told you what is the general expression. C of n is always equal to C of minus 1 to conjugate, or C of n conjugate is equal to C of minus n. So this one I have already told you, right? So this is a very important property. And suppose if f of t is an even function, then C of n is equal to C of minus n. If f of t is an odd function, then C of n is equal to minus of C of minus n. But this is a overall condition. If f of t is odd, then C of n is equal to C of minus n. And if f of t is even, then C of n is equal to C of minus n. If f of t is odd, then C of n is equal to minus of C of minus n. See, suppose f of t is a periodic signal which is having a triangle of T1. For this T1, the Fourier's coefficient is Cn. And g of t is also a periodic signal for time period, it's having time period T2. And on this, the Fourier's coefficient defined as Bn. So now, we are having different time periods. So now I want to basically make on the same time period, I want to find the Fourier's coefficient for these two signals on a common time period, which is T is the LCM of the T1 and T2. So based on this, I got the new Fourier's coefficient for the f of t and g of t, which is f of t is having a Fourier's coefficient Cn dash, and g of t is having a Fourier's coefficient Tn dash on the same time period. Now go for the linear combination of these two signals, and the resulting signal is also a periodic signal which is having taken by same time period t, and the resulting signal Fourier's coefficient will be a1 into Cn dash plus a2 into Tn dash. So these points always you have to keep in your mind. So these things always you have to keep in your mind. So finally, let me repeat here. We are going to discuss some of the important properties of the Fourier's coefficients, which is if for f of t, the Fourier's coefficient is Cn, and for f of t plus or minus t naught, the Fourier's coefficient is Cn into e to the power of plus or minus j n omega naught t naught. And for f1 of t, the Fourier's coefficient is Cn1, and for f2 of t, the Fourier's coefficient is Cn2. So both are defined on the same time period. And if you go for the linear combination of these two signals, these two periodic signals is also a resultant periodic signal having the same time period, which is a1 into f1 of t plus a2 into f2 of t, we will have the resulting Fourier's coefficient, which is a1 into Cn1 plus a2 into Cn2. Similarly, for f of t, if the Fourier's coefficient is Cn, then kth derivative of f of t will have the Fourier's coefficient jn omega naught all the power of k into Cn. Jn omega naught all the power of k into Cn. For f of t, if the Fourier's coefficient is Cn, then a plus f of t means whether you are adding the BC for the f of t means the signal is going to shift either upward or downward based on the value of a. So the Fourier's coefficient will never change, but only the DC value is going to get changed for this new signal. So Cn for n not equal to 0, and a plus c0 for the n is equal to 0. So only the DC terms is going to get changes, but the remaining Fourier's coefficient will remain as it is. So for f of t, the Fourier's coefficient is Cn, then I'm taking this into z of t, which is the f of minus t. It will have the new Fourier's coefficient Bn, which is equal to C of minus Bn. So f of t is Fourier's coefficient is Cn, so f of minus t will have the Fourier's coefficient C of minus Cn. If of C, I already told you, Cn is nothing but complex conjugate C of minus n, or C of minus n is nothing but it's a complex conjugate of C of n. I've already told you this one so many more times, because Cn is equal to a by 2 minus j dn by 2, and C of minus n is equal to an by 2 plus j bn by 2. So based on this, both are, one is the complex conjugate of the other and other is the complex conjugate of the other. So if f of t is even, then C of n is equal to C of minus n. If f of t is odd, then C of n is equal to minus of C of minus n. Suppose f of t is a periodic signal, on the time period of, so f of t is a periodic signal, for a time period of t1, we have defined the Fourier series coefficient Cn. And g of t is also periodic signal, for time period of t2, we have defined the Fourier series coefficient Dn. So now, basically, I want to define this Fourier series coefficients only on the same time period. The time period is the LCM of the individual time periods. Then, based on this time period, for these signals, I have got the Fourier series coefficient is for above the Fourier series, the new Fourier series coefficient is Cn dash, and for g of t, the new Fourier series coefficient is Dn dash. So if we go for the linear combination of these two signals, it is also related signal, it is also periodic signal at the same time period t, then the resultant Fourier series coefficient will be a1 into Cn dash plus a2 into Dn dash. So these things always you have to keep in mind. So always, whenever you go for the linear combination of the signals, try to figure out the, and a common time period, try to figure out those signals, those periodic signal, those Fourier series coefficients, and then go for the linear combination of that Fourier series coefficients you can go. So these properties always you have to keep in your mind. So these are the important properties of the Fourier series coefficients always you have to keep in your mind. In the examinations, they may ask you regarding the, they may ask regarding the properties they may ask. That is the reason I am specified in a very detailed manner. Now, the next concept that we are going to discuss is about the Dirichlet conditions for the Fourier series existence for periodic signal. So, the Dirichlet conditions for the Fourier series existence for the periodic signal. So, we are going to discuss about the Dirichlet conditions for the Fourier series existence for a periodic signal. Suppose there is some periodic signal. So there are some constants are there. If these constants are satisfied, then we can say the Fourier series expression is going to, that we are going to get for the periodic signal. So what are those? Which was given by the Dirichlet. So that is the reason we say these are the Dirichlet conditions for the Fourier series existence for periodic signal. So basically, suppose there is a periodic signal. If the signal has satisfied some conditions, then definitely we can say the Fourier series is going to exist for the periodic signal. So what are those conditions? Those conditions are given by Dirichlet. So there is the reason it is called as the Dirichlet conditions for the Fourier series existence for periodic signal. So listen carefully. Signal f of t must be absolutely integrable in one of its time period. So suppose f of t is a periodic signal. So in one time period, means in one cycle, it must absolutely integrable. Absolutely means the magnitude value. The magnitude value, we can say like this. So listen carefully. The magnitude value of f of t dt in just only one time period should you are going to get a finite value. So therefore, the signal f of t must be absolutely integrable in one of its time period. So in just only one time period, mod of f of t dt, if you do this one, then you should get a finite value. So this is one of the condition of the Dirichlet conditions for the Fourier series existence. Signal f of t must be absolutely integrable in one of its time period. Suppose that you take some f of t is a periodic signal. So take only for one time period and do the absolutely integrable, means the magnitude of the f of t to integrable in a one time period, which is integration over t mod of f of t dt. If you do this one, you should get a finite value. Then there must be only finite number of maxima or minima in a given time period. So in a given time period, the signal should have a finite number of minima and a finite number of maxima. So if you take a given in a given time period, the signal, the periodic signal f of t should have the finite number of minima as well as a finite number of maxima. The next point is there must be finite jump of finite discontinuous in a given time period. So there must be finite jump of finite discontinuous in a given time period. So there must be a finite jump of finite discontinuous in a given time period. So basically, what is the meaning of discontinuity? Sudden jump. So listen carefully. There is a sudden jump like this. So there is a sudden jump like this. So therefore, it should be a finite value. So there must be finite jump of finite discontinuous. Basically, there must be finite jump of finite discontinuous, or we can say finite discontinuous. Finite discontinuous, not of. It is or. Because there must be finite jump. Finite jump is also called as a finite discontinuity. Finite discontinuity. So then the discontinuity is there. So in a given time period. So it should be or, not of. So there must be a finite jump or finite discontinuity. Sudden jump is nothing but discontinuity. Some discontinuity is there. So therefore, there must be a finite jump of finite discontinuities in a given time period. So what are the three conditions? The three conditions are a signal f of t must be absolutely integrable in one of its time period. Means interest over the t mod of f of t dt should be, you should get a finite value, and there must be only finite number of maxima or minima in a given time period, and also there must be a finite jump or finite discontinuous in a given time period. So these are the conditions that must be satisfied by the f of t, or it's basically a periodic signal. So the signal f of t should be absolutely integrable in one of its time period, which is interest over the mod of f of t dt. You should get a finite value, and there must be only finite number of maxima as well as a finite number of minima in a given time period, and also there must be finite jump or a finite discontinuous in a given time period. So what I'm trying to tell you is very simple. Suppose if we take some periodic signal f of t, so if we say some periodic signal f of t, first you have to see whether the signal f of t is satisfied these conditions or not. So what is the first condition? In a given time period, you should do the absolute integral of the function f of t, then you should get a finite value. And the thing here, in a given time period, it should have finite number of maxima and finite number of minima, and also you should check whether it has basically a finite discontinuous or finite jump. All these three conditions you need to check. If all these three conditions are satisfied, means definitely the Fourier series expression is going to, we are going to get for the periodic signal. So we can say what are the three conditions? The Dirichlet conditions for the Fourier series existence for periodic signal is the signal f of t must be absolutely integrable in one of its time period, which is interest over the t mod of f of t dt. You should get a finite value, and there must be only finite number of maxima as well as a minima in a given time period, and there must be a finite jump or finite discontinuous in a given time period. So in simple words, I can say, suppose there is a f of t which is a periodic signal. So now we need to check whether for this function, whether a Fourier series is going to exist or not. The first thing is first you have to check the Dirichlet conditions. There are three Dirichlet conditions. What are those? Which are in a given one cycle, try to figure out the absolute integral of the function. If you are going to get a finite value, so the first condition is satisfied. And what is the second condition? There must be a finite minima and a finite maxima in a given one cycle, and also there must be a finite jumps or finite discontinuous in a given one cycle. If all these three conditions are satisfied, means the Dirichlet conditions are successfully satisfied, then the Fourier series is going to exist for that function, for that graph, or that signal. So now here, what is important note here? If any signal sufficiently satisfies all these three conditions, then compulsory Fourier series expression exists. Suppose if you take any signal f of t, it's a periodic signal. So now we have checked all the three conditions of the Dirichlet. So finally, first condition is satisfied, second condition is satisfied, and third condition is satisfied. Then definitely the Fourier series expression is going to hold that is going to occur for this function f of t. So if all the three conditions of the Dirichlet are satisfied, then definitely the Fourier series expression is going to occur. These conditions are only the sufficient conditions for the existence of Fourier series expression, but not necessary. So these are the sufficient conditions only. Suppose a periodic signal f of t has satisfied all the three conditions, then definitely the Fourier series will exist. Suppose there might be some other function f of t, this may not satisfy. Suppose this may satisfy first condition, but it may not satisfy the second and third. Then also the Fourier series can exist. And also the Fourier series expression can exist. So we can say these are the only sufficient but not the necessary condition. Is only sufficient. So therefore we can say here there are some functions, even though they are not satisfying Dirichlet conditions, still the Fourier series is going to exist. But if any function is going to satisfy all these conditions, then definitely the Fourier series will exist. So this is what I am trying to tell you. So listen, I will draw a simple table here. So Dirichlet conditions. So if they are satisfied, then the Fourier series will always exist. So Fourier series will always exist. Conditions are satisfied. So here conditions are satisfied. Suppose if the Dirichlet conditions are not satisfied, then the Fourier series may exist or it may not exist. So listen carefully. Suppose if the Dirichlet conditions are satisfied, then compulsory the Fourier series will exist. Suppose if the Dirichlet conditions are not satisfied, then the Fourier series may exist or may not exist. So it may exist or it may not exist. So this is a table you have to keep in your mind. So therefore we can say this Dirichlet conditions are only the sufficient conditions but not the necessary conditions for the existence of the Fourier series. So this is what I am trying to tell you. So this is what I am trying to tell you from all these times. So if that is the reason that the Dirichlet conditions are called as only if they are for sufficient conditions but not the necessary conditions. So if the Dirichlet conditions satisfied means definitely the Fourier series is going to exist for the expression. Suppose if the Dirichlet conditions are not satisfied, then there may be a chance of Fourier series may exist or may not exist. So this is what I am trying to tell you. So therefore we can say clearly, if the Dirichlet conditions, if all the Dirichlet conditions are satisfied, then the Fourier series will always exist. It will always exist. Compulsory will exist. Suppose if these conditions are not satisfied, then there may be a chance of existing or not existing. So this is what I am trying to tell you. So there is a reason that Dirichlet conditions are called as the sufficient conditions but not the necessary conditions. So finally I can say, if all the Dirichlet conditions are satisfied, then compulsory the Fourier series expression will exist. Suppose if the Dirichlet conditions are not satisfied, then the Fourier series may exist or it may not exist. So this is what I am trying to tell you. So if any signal sufficiently satisfies all these three conditions, then compulsory the Fourier series expression exists. These conditions are only the sufficient conditions for the existence of the Fourier series expression but not necessary condition. So I have already told you, if all the Dirichlet conditions are satisfied, then the Fourier series will compulsory exist. Suppose if the Dirichlet conditions are not satisfied, the Fourier series may exist or it may not exist. So this is what I am trying to tell you. So now let's go for the next concept. So what's the next concept? The Fourier transform for a periodic signal. So we are going to find the Fourier transform for a periodic signal. So for a periodic signal, we are going to find the Fourier transform. So for a Fourier transform. So this is a thing always you have to keep in mind. So Fourier transform for a periodic signal. So Fourier transform for a periodic signal or periodic signal. There is small confusion here. Is basically a Fourier series is for the periodic signal. So Fourier transform for the aperiodic signal. I guess it is a aperiodic signal, not a periodic signal. So this is a aperiodic signal. Aperiodic signal means we can say, so we can say it is a, so we can say basically what is the meaning of this one? So basically we are going to discuss the Fourier transform for a periodic signal only. So this is for a periodic signal we are going to discuss. So we are going to discuss the Fourier transform for periodic signal. For a periodic signal. So periodic signal nothing but it's a real signal. So real signal. So listen carefully. Here, suppose f of t is equal to 1 by 2 pi integration over the omega is equal to minus into plus infinity f of omega e to the power of j omega t d tau d omega and f of j omega or f of omega is equal to integration over the t is equal to minus into plus infinity f of t e to the power of minus j omega t dt. So this formula you have to remember. See basically what I am trying to tell you, it is a aperiodic signal. It is a aperiodic signal. A small correction. Here aperiodic means non-periodic. So the Fourier transform for aperiodic or non-periodic signal. So aperiodic means, so listen carefully. Aperiodic means we can say not repeating, or can also call this as the non-periodic. So non-periodic. So if you see clearly, for periodic signals, we have applied the Fourier series. So Fourier transform is for the aperiodic signal. So listen carefully. So for a periodic signal, we have discussed the Fourier series. For aperiodic signals, we are going to discuss the Fourier transform. So this is what concept you have to keep in your mind. So for periodic signals, we have learned about the Fourier series. For aperiodic signals or non-periodic signals, we are going to discuss the Fourier transform. So in this case, we are going to discuss the Fourier transform for the aperiodic means non-periodic signals. These are the real signals because there is no complex term. So what is the formula? This formula you have to remember. F of t is equal to 1 by 2 pi integration over the omega is equal to minus into plus 50 f of omega e to the power of j omega t d tau. And f of j omega or f of omega integration over the t is equal to minus into plus 50 f of t e to the power of minus j omega t d tau dt. As I already told you, if you know the Laplace transform of a signal f of t is equal to, So the Laplace transform f of t is f of s is equal to integration over t is equal to minus nt by 70 f of t to the power of minus st dt. So if you want the Fourier transform, is replace s by j omega. So we are going to get the Fourier transform, which is f of j omega or f of omega, which is equal to integration over t is equal to minus nt by 70 f of t to the power of minus j omega t dt. So this is a Fourier transform of the signal f of t. So suppose if you want the reverse, means f of t is equal to 1 by 2 pi integration over here t means it will become omega. Omega is equal to minus nt by 70. Here dt means it will become d omega. Here f of t means here f of omega, and here minus means here plus. So this is the thing you have to keep in the mind. So let me write the formulas here. So then you can easily able to understand what I am trying to tell you. So let me write the formulas here, so that you can easily able to understand. So you know the Fourier transform. So let me write here the formula. Let me choose the other. So I think the page is not responding. Just wait a minute so that we can make things. Now it's responding. Let me write the formula. So let me write the formula. See, I already told you what is the Fourier transform. The Fourier transform is either f of j omega, or we can say f of omega. And now it is same is equal to f of omega is equal to. So we can say integration over the t is equal to minus infinity to plus infinity. Here f of t into e to the power of minus j omega t dt, right? So you have to remember this one. So do the reverse. How to reverse means f of t we are going to write. So I already told you here t means it will become omega, because we are taking inside omega. Here inside we are taking t, right? So now we are doing with respect to omega. So f of omega. So here omega is equal to minus infinity to plus infinity. Then minus means it will become plus here. So plus, then dt means it will become d omega, and you have to keep an extra factor of 2 pi. That's it. So therefore, if you remember this one, it is easy to get this one. So in f of omega we are doing in place of f of t. So now I want to write the reverse. F of t in terms of f of omega. So omega means integration over the omega. Omega is equal to minus into plus into f of omega. Here minus plus here plus. Here dt means here d omega. And you have to keep an extra factor of 1 by 2 pi. So this is what I am trying to tell you. So same thing. So now what we will do, so this Fourier transform, if you do the simplification, we are going to get basically complex number, we are going to get real number as well as imaginary number. So f of omega is equal to the real part of omega plus j into imaginary part of omega. Because you are going to get a complex number, so there will be real as well as the imaginary term. So that is the reason I have taken f of omega is equal to the real part of omega plus j into imaginary part of omega. So now, if you see clearly, the real part of omega is always a even nature. It will be always a even. The real part of omega will be always even. It is going to satisfy the even nature, which is FPR of omega is equal to FPR of minus omega. This is basically, it is always a even nature. And this one is always odd nature, which is F imaginary of omega is equal to minus of F imaginary of minus omega. So this is always going to satisfy the odd nature, and this is going to satisfy the even nature. So therefore, listen carefully. So this is going to satisfy the even nature, and this is going to satisfy the odd nature. So what we can say, FPR of minus omega is equal to FPR of omega, and FAM of minus omega is equal to minus of FAM of omega. So this real part is going to satisfy the even nature. It is always a even nature, and the imaginary part of omega is always a odd nature. So we can say the real part of omega is always going to satisfy the even nature, and the imaginary part of omega is always it is going to satisfy the odd nature. Then what is going to happen for this one? Let's check here. So let's simplify here. So you can see what is the f of omega, as I already told you, f of omega is equal to FPR of omega plus j into f imaginary part of omega. So replace omega by minus omega. So replace omega by minus omega. Then see what is going to happen. So if I replace omega by minus omega, then what I am going to get? F R of minus omega plus j into f imaginary of minus omega. So you know, as FPR is a real, it's a real nature. So FPR of minus omega is equal to FPR of omega only. Whereas this one is a odd nature. So it will become minus j f imaginary part of omega. So this is f of minus omega. So if you see clearly, this is nothing but the complex conjugate of this one. So this is nothing but the complex conjugate of this one. Therefore, f of minus omega. So f of minus omega is equal to f of omega whole conjugate. So you can do the reverse also. You can do reverse also. It is identical to conjugate. So doing the conjugate on both sides, then you are going to get like this, which is f of omega. So this is what I am trying to tell you. So f of minus omega is the f of omega whole conjugate, and do the conjugate on both sides, then we are going to get f of minus omega whole conjugate is equal to f of omega. Because if you do the conjugate on both sides, the conjugate cancels. So we are going to get this one. So this is what I am trying to tell you. So f of omega is equal to f of minus omega whole conjugate. Because you can say it is a even conjugate. So we can say it is a even conjugate because f of omega is f of minus omega whole conjugate. So that is the reason we say it is a even conjugate. Even conjugate. Because it is a complex set, is at the complex signal set. So therefore even conjugate. I have already told you for complex signals what is a even conjugate and odd conjugate. I have already told you for the time domain. For time domain I have already told you if any signal, see for the real signals what is the even nature, f of t is equal to f of minus t, even nature for real signals, and for odd nature means f of minus t is equal to minus of f of t. So I have already told you right, this is for real signals. For real signal even nature and real signal odd nature. Suppose for if you want to know for the odd signal, for the complex signals the even nature and odd nature is, you have to replace f of minus t by f conjugate of minus t. So replace f of minus t by f conjugate of minus t. So you will also conjugate. So in place of t, now substitute omega, then what you are going to get? So f of omega is equal to f of minus omega whole conjugate. So this is called as the even conjugate for the complex signals, and f conjugate of minus omega is equal to minus f of omega. So this is the odd conjugate. So this is the even conjugate and this is the odd conjugate for the complex signals. So here they are going to satisfy this property, right? So they are going to satisfy this property. F of omega is equal to f of minus omega whole conjugate. So this is called as the even conjugate. Suppose if there is a minus means it will become odd conjugate. So these things always you have to keep in mind. So f of t is equal to f of minus t means for real signal it is a even nature, and f of minus t is equal to minus of f of t means that is for real signal it is a odd nature. But if you want complex means replace f of minus t by f conjugate of minus t. So if f of t is equal to f conjugate of minus t, this is a even conjugate, even complex signal, and f conjugate of minus t is equal to minus of f of t means this is a odd conjugate signal or even conjugate of odd conjugate. See, this is a even complex signal is also called the even conjugate signal, and is a odd complex signal or odd conjugate signal. You can call it anything. So replace t by omega, then we are going to be like this. So this is called as the even conjugate signal, and this is called as the odd conjugate signal. As the previous one what you have studied, this is going to satisfy this property. So this is called as the even conjugate. Even conjugate. So that is the reason I have written here. So finally I can say the real part of this omega is the even nature and is the odd nature, and overall this is the even conjugate. It is going to satisfy the even conjugate. So f of omega, as you can see clearly, it has the real part and imaginary part. So you can convert this is a rectangular format. So if you convert to the polar format, it will have some magnitude as well as the phase angle. So f of omega is equal to mod of f of omega phase angle of f of omega. So because I have basically converted the real part, the rectangular part to polar part. So it will have magnitude as well as a phase angle. As omega is varying from minus to plus infinity. So omega is varying from minus to plus infinity. So basically, this magnitude spectrum is always a even nature. It is always a even nature, whereas the phase angle is always a odd nature. So therefore, the magnitude spectrum is always going to give you an even nature, whereas the phase angle is going to give you the odd nature. So this is a very general thing. We no need to even think about this one. As you can see clearly from that part. So therefore, we can say that as f of omega is equal to mod of f of omega, phase angle of f of omega. So the magnitude spectrum, which is mod of f of omega, is always going to have an even nature, whereas the phase angle, which is the phase angle of f of omega, will have an odd nature with respect to omega. So this is what always you have to keep in your mind. Now let's do some more analysis. We can say, suppose if f of t is a real signal with even nature, then what is going to happen? Suppose if f of t is a real signal with even nature, then what is going to happen? So if f of t is a real signal, if if f of t is a real signal with even nature, then what is going to happen that we are going to see. Basically, whatever the things that we are going to study, we will transform for a periodic or non-periodic signal that we are studying, right? So, here f of t is a real signal with even nature. Even nature means we can say f of minus t is equal to f of t. Then what is going to happen? So, as you can see clearly here, then f of omega will be purely real. It will be purely real. Suppose if f of t is a real signal with odd nature, then f of omega will be purely imaginary. Suppose if f of t is a real signal, neither even nor odd nature, then f of omega will be complex nature. So this thing you don't have to remember this one also. Suppose if you take a periodic signal or non-periodic signal and f of t is a real signal with even nature, then f of omega is purely real. Suppose if f of t is a real signal with odd nature, then f of omega is purely imaginary. Suppose if f of t is real signal neither even nor odd nature, then definitely f of omega is basically complex nature. It will be complex nature. So now listen carefully. What I am trying to tell you. Suppose if you take a periodic signal or non-periodic signal, and if f of t is a real and even nature, then f of omega is purely real. If f of t is a real signal and with odd nature, then f of omega is purely imaginary. Suppose if f of t is a real with neither or nor even, then f of omega is purely it's a basically complex nature. It will have real part as well as the imaginary part. So now let's I have given a small table. So listen carefully. This is a time domain of f of t and it's a frequency domain. So for a periodic signal or non-periodic signal, see I have given here. Suppose if f of t is a real as well as even, so f of t is a real as well as even, then what is going to happen? Just now we have discussed, if f of t is a real and even, then f of omega will have only the real part. So f of omega will be purely real. Real means, the real part is always even in nature. Just now we have discussed that the real part is always even in nature. So even in nature. Suppose if f of t is real as well as odd, then what is going to happen? So I already told you, if f of t is real and odd, then f of omega is purely imaginary. So f of omega is purely imaginary. Purely imaginary is nothing but that the imaginary part of omega is odd nature. So it will be odd nature. Now if you know these two things, then the remaining thing is very simple. So if you know these two things, then the remaining things are very easier. So remaining things are very simple. So listen carefully. So here what I did, here I replace real by imaginary, then even. So replace real by imaginary and remaining thing is same. Here I replace real by imaginary and remaining thing is same. So we also replace imaginary by real. So imaginary by real. So here real means, say here real, take it out and keep imaginary. Here take it real replaced by imaginary, and here what I am trying to tell you is very simple. Here real is there means opposite is imaginary. Here real is there means opposite is imaginary. Here real is there, what is the opposite? Imaginary. Here imaginary is there, what is the opposite? Real. That's it. And remaining everything is same. So if you know these two things, getting these two things is very simple. So real means what is the opposite? Imaginary. Here real means what is the opposite? Imaginary. Here real is there, what is the opposite? Imaginary. Here imaginary is there, what is the opposite? Real. So if you know these two things, getting these two things is very easier. So therefore what I am trying to do is very simple. Is a time domain function of f of t and is a frequency domain of f of omega. Suppose if f of t is real as well as even, then what is going to happen? I've already told you, whenever the f of t is real and even, then f of omega is purely, it will have only the real part. And the real part is by default it is a even nature. And if f of t is a real as well as odd, it's a real signal with odd nature, then f of omega is purely imaginary. Imaginary part is it is an odd nature. And also then if you know these two things, just replace real by imaginary and replace real by imaginary. Opposite. Here real means opposite is imaginary. Here imaginary means opposite is real. Just replace the opposite. And remaining things are same. Here even. Here odd, here also odd. This is what I am trying to tell you. So finally I can say, suppose if f of t is a real signal with even nature means f of omega is purely real. There is no imaginary part. And purely real means by default it is a even nature. Suppose if f of t is a purely real with odd nature, then what is going to happen? Then by default we can say it is a oddness. By default only the imaginary part is going to get present, odd part is 0. So the real part is 0, only the imaginary part is going to get present, and imaginary part is, it is a odd nature. So therefore, we can say that these things always you have to keep in mind. So if you know these two things, these two things is very simple. Replace, just take the opposite of this one. Real opposite is imaginary, real opposite is imaginary, and remaining things are same. Real opposite is imaginary, and imaginary opposite is real, and remaining things are same. So these things always you have to keep in your mind. So like this always you have to analyze. Like this always you have to analyze. Now we will discuss about the other concept, which is the Fourier transform for the periodic signals. So after now we have learned about the Fourier transform for the periodic signals or non-periodic signal. But now we will discuss for the Fourier transform for the periodic signals that we are going to discuss very soon. Very clear. Periodic signal means the signal is going to repeat after certain amount of time. Those signals are called as the periodic signals. So we are going to find the Fourier transform for the periodic signals that we are going to discuss in a very detailed manner. The Fourier transform for the periodic signal in the time period t is, suppose I have taken some periodic signal, it is having a time period of t. So for this I want to figure out what is the Fourier transform, which is I have already told you. So if I figure out the Fourier transform, we are going to get the Fourier transform, which is the complex number. I have already told you it's a complex number. So it will have the magnitude as well as the phase angle. So f of omega is equal to mod of f of omega and the phase angle of f of omega. This I have already told you, right? So because the Fourier transform will have the real part and complex part, so definitely it will have magnitude as well as the phase angle. So f of omega is equal to mod of f of omega and phase angle of f of omega. So in the case of Fourier, the periodic signal, there will be Fourier series coefficients which are Cn. So Cn I can write. Cn is also a complex number. Cn is also a complex number. So it will have the magnitude as well as the phase angle. So mod of C of n and phase angle of C of n. So therefore, the Fourier series coefficient will also have the magnitude part as well as the phase angle part. So Cn is equal to mod of Cn and phase angle of Cn. So now listen carefully that suppose in the magnitude part of the Fourier transform, mod of f of omega at omega is equal to n omega naught, which is equal to 2 pi times of mod of Cn. So we can see clearly the mod of f of omega is equal to 2 pi times that mod of Cn at a corresponding omega is equal to n omega naught. So whereas here omega you have to replace by n omega naught. So suppose if you want n is equal to 1 means here you take n is equal to 1. Suppose if you want here n is equal to 2 means here n is equal to 2. So therefore you can see clearly at omega is equal to n omega naught. Suppose if you substitute n is equal to minus 1, then here you have to use c of minus 1. You just take the magnitude part. So therefore these things always you have to keep in mind. So mod of f of omega at omega is equal to n into omega naught is equal to 2 by times of mod of Cn. And the phase angle of f of omega is equal to the phase angle of Cn. So both are equal. The phase angle of f of omega is equal to the phase angle of Cn at omega is equal to n omega naught. So this is the value of omega is equal to n omega naught. So if you know the Fourier series coefficient, so if you know the Fourier series coefficient, take that magnitude and take that phase angle. So the magnitude part multiply with 2 pi and the phase angle take it as it is. So from that we are going to get the magnitude spectrum as well as the phase angle spectrum also we are going to get. And what is the value of n? N is nothing but its value is from minus infinity plus infinity. Just now we have discussed as because here n is for this value, right? So this is for n. So Fourier series coefficient is defined for n is equal to minus infinity plus infinity. So this n value is defined from n is equal to minus infinity plus infinity. So because of this, we are going to get n values is lying from minus infinity plus infinity. This n value we are going to get from the Fourier series coefficient. So these are only integers. Whereas omega value we are going to get from minus infinity plus infinity any value. These are only integers, but omega can be any value. So omega can be any value, whereas n is always a purely integers. And what is omega naught? Omega naught is equal to 2 pi by t. T is the time period of the periodic signal. So therefore, finally what I am going to tell you is very simple. Basically, suppose if you take a periodic signal which is having a time period of t, and if you want to find the Fourier transform for the periodic signal, first thing is you have to find the Fourier series coefficient for the periodic signal, which is Cn is equal to mod of Cn and phase angle of Cn, because the Fourier series coefficient will have the complex number, so it will have the magnitude as well as the phase angle. So because of that, we can say it will have Cn is equal to mod of Cn and phase angle of Cn. And then what is the Fourier transform? You know the Fourier transform is also complex number. It will have the magnitude as well as phase angle. So f of omega is equal to mod of f of omega and phase angle of f of omega. So if you know this value, we can get this value by this relation. So mod of f of omega and omega is equal to n omega naught is equal to 2 pi times the mod of Cn, and the phase angle of f of omega at omega is equal to n omega naught is equal to the phase angle of Cn. And value we are going to get from the Fourier series coefficient, and its values ranging from minus infinity to plus infinity. These are only integers. Whereas the omega value is varying from minus m to plus infinity, that we are going to get from the Fourier transform, and it can be any value, and omega naught is equal to 2 pi by t. So t is a fundamental time period of the periodic signal. So from that we are going to get the fundamental frequency omega that we are going to get. So by this way, for any periodic signal, we can get the Fourier transform. Just by knowing the Fourier series coefficient, the magnitude and the phase angle, we can get the Fourier transform also we can easily get. So this is what I am trying to tell you. Now we are going to discuss the other concept, which is the Fourier transform of the signals. So we are going to discuss the Fourier transforms of different signals. So for each and every signal, we are going to discuss the corresponding Fourier transform we are going to study in detail. So you can see for the first signal e to the power of minus at into u of t. So e to the power of minus at into u of t, this signal has the Fourier transform 1 by a plus j omega. So e to the power of minus at, so I have already told you, listen carefully. For e to the power of minus at means we can say e to the power of minus at into u of t. So I have already told you for this, what is the Laplace transform? So what is the Laplace transform? So Laplace transform, as I already told you. So what is the formula? 1 by s plus a. So 1 by s plus a is the Laplace transform. So in the Laplace transform, always replace. If you want the Fourier transform is in the Laplace transform, substitute s is equal to j omega, then we are going to get the Fourier transform. So n plus of s, substitute s is equal to j omega, then we are going to get the Fourier transform. So therefore 1 by j omega plus a, or you can write 1 by a plus j omega also you can write. So this is the Fourier transform for the e to the power of minus at into u of t. So e to the power of minus at into u of t means like this waveform we are going to get. So this is our waveform that we are going to get. So let me go for the another sketch so that we can easily able to. So see, so this is the e to the power of minus at into u of t. Right? So these things always you have to keep in your mind. So therefore we can say for e to the power of minus at into u of t, the Laplace transform is 1 by s plus a. So if you want the Fourier transform is in the Laplace transform substitute s is equal to j omega, then we are going to get 1 by j omega plus a, or you can write 1 by a plus j omega. And if you want to know the waveform for e to the power of minus at into u of t, as you can see clearly here, the waveform you are going to get like this, like a decaying signal. So like decaying signal, whereas for t less than 0, its value is equal to 0. So this is what I am trying to tell you. So this is what I am trying to tell you. So these things always you have to keep in your mind. Now let's go for the another signal. This is the second signal is e to the power of at into u of minus t. So for e to the power of at into u of minus t, the Laplace Fourier transform is 1 by a minus j omega. 1 by a minus j omega. So if you want the picture, then let me show you here. So we can say, so e to the power of at into u of minus t. So u of minus t, it will have the Laplace transform which is 1 by a minus j omega. 1 by a minus j omega. So if you want to draw the graph, so how the graph is going to look like? So if you see the picture, it will be like this value. So like this you are going to get. So this is the picture that you are going to get. So this is the picture which is e to the power of at into u of minus t. So this is a picture that you are going to get. So this is a t at minus infinity and t at infinity. So this is a picture that you are going to get here. So these things always you have to keep in your mind. So if you see clearly, for e to the power of minus at into u of t, the Fourier transform is 1 by a plus j omega. Suppose if you want the Fourier transform for e to the power of at into u of minus t, then the Fourier transform is 1 by a minus j omega. So I want you to remember this formula. For f of t, if the Fourier transform is f of omega, then f of at, I already told you for f of at, what is the Fourier transform? It is 1 by mod a into f of omega by a. So this formula, as I already told you so many number of times. Right? So for f of t, the Fourier transform is f of omega. Then f of at will ask the Fourier transform, which is 1 by mod a into f of omega by a. Here a can be positive or a can be negative. So a can be positive or a can be negative also. So if you see clearly, suppose if I substitute a is equal to minus 1, then what I am going to get 1 by mod of minus 1. Mod of minus 1 is 1, so 1 by 1 is 1. And f of omega by minus 1. So omega by minus 1 is minus omega. So therefore, f of minus t means the Fourier transform is f of minus omega. So for f of t, the Fourier transform is f of omega. So for f of minus t, the Fourier transform is f of minus omega. So here this is f of t and the Fourier transform is f of omega. So if you want this one is replace t by minus t. So if you replace t by minus t, then you are going to get this value. So if you replace omega by minus omega, so you are going to get this value. So therefore always remember, for f of t, the Fourier transform is f of omega. Then f of at, the Fourier transform is 1 by mod a, f of omega by a. A can be positive or a can be negative. So we can say f of minus t is nothing but its Fourier transform is f of minus omega. So therefore we can say finally we can say the conclusion for these two things, for e to the power of minus at into u of t, the Fourier transform is 1 by a plus j omega. So I already told you, when f of t has the Fourier transform f of omega, then f of minus t means replace t by minus t, then you are going to get like this, right? So for this one, the Fourier transform is a plus omega by minus omega, then we are going to get a minus j omega. So this is what I am trying to tell you. So now let's go for the other signal. The other signal is e to the power of minus at u of t plus e to the power of at u of minus t. It is nothing but summation of two previous signals. So this signal plus this signal is nothing but we can write like this e to the power of minus a mod t, because for t greater than 0, mod t will become plus t. So you are going to get this one. For t less than 0, mod t will become minus t. Then you are going to get this signal. So therefore you can say, if we add the summation of the two previous signals, add the summation of the two previous Fourier transform, that's it. So if we add the summation of two previous Fourier transform, 1 by a plus j omega plus 1 by a minus j omega. So the LCM is a square minus j omega whole square means minus of j omega whole square. J square is minus 2a plus omega square. So take it a minus j omega plus a plus j omega. J omega cancels, we are going to get 2a by a square plus omega square. So if you do the summation of two previous signals, then do the summation of two previous Fourier transforms also for the corresponding signals. So we are going to get 2a by a square plus omega square. So this is what I am trying to tell you. So if you do the summation of the two previous signals, so do the summation of the two previous Fourier transform, then we are going to get this one. So if you do the subtraction of these two signals, e to the power of minus at u of t minus e to the power of at u of minus t, then also do the subtraction of these two Fourier transform, then we are going to get finally minus 2 j omega by a square plus omega square, just the subtraction of these two things. So we are going to get. So if you add these two things, please add these two things. If you subtract these two things, please subtract these two things. So this is the Fourier transform always you are going to get. So I want you to remember this one. If you remember this one, you can get for all these things very easily. E to the power of minus a dv of the Fourier transform is 1 by a plus j omega. So for this one means replace t by minus t. So replace omega by minus omega, you are going to get this value. So if you add these two signals, then we are going to get this one. So add these two Fourier transform, we are going to get this value. Subtract these two things, we are going to get this signal. So subtract these two things, we are going to get this one. So this is what I am trying to tell you. So now let's go for the other signal. The signum of t. Signum of t means u of t minus u of minus t. So u of t minus u of minus t. So now for u of t, if you want u of t means substitute here a is equal to 0. Here a is equal to 0. If you substitute here a is equal to 0, then what you are going to get? 1 by j omega you are going to get. And similarly, to see basically here, suppose if you take this relation, right? So you take this relation. Here substitute a is equal to 0. Substitute here also a is equal to 0. Then what is going to happen? We are going to get u of t minus u of minus t, right? So in place of a substitute 0. Here also in place of a substitute 0. So therefore you are going to get minus 2 omega j by omega square. So omega by cancels, we are going to get minus 2 j by omega. So this is what I am trying to tell you. So finally listen carefully. Here in place, see I have know this formula. So in place of a I have substitute 0, then I got this signal. In place of a I substitute 0, then I got this Fourier transform. So signum of t. So signum of t is nothing but u of t minus u of minus t. For this the Fourier transform is minus 2 j by omega. So this is what I am trying to tell you. So if you remember these two things, It's very simple. So if you remember this one thing, then you can get this value by v plus p minus p. Then you are going to get v plus omega by minus omega, you are going to get this value. So if you add these two things, we are going to get this one. If you add these two things, we are going to get this one. If you subtract these two things, we are going to get this value. If you subtract these two things, we are going to get this value. So in place of a, if you substitute 0 for this previous equation, then we are going to get this one, which is nothing but signum of t. Signum of t means for t greater than or equal to 0, its value is equal to 1, and for t less than or equal to 0, its value is equal to minus 1. So this is the Fourier transform that we are going to get. So now for the delta of t, the Fourier transform is 1. So this is what thing you have to remember. So for Laplace transform also its value is equal to 1. So Fourier transform is also equal to 1. So this is what I am trying to tell you. So therefore we can say that the delta of t, the Fourier transform is nothing but 1, because the Laplace transform is also 1. So Fourier transform is also equal to 1. So for a means it's a constant signal. For this, the Fourier transform is 2 pi a delta of omega. So 2 pi a delta of omega. So this one you have to remember. So for a means 2 pi a delta of omega. 2 pi a delta of omega. And e to the power of j omega naught t, the Fourier transform is 2 pi omega of omega minus delta of omega minus omega naught. So for e to the power of j omega naught t, the Fourier transform is 2 pi into delta of omega minus omega naught. So if you want cos omega naught t, you know what is the formula? You know cos omega naught. So let me tell you here. E to the power of I theta is nothing but cos theta plus I sin theta. So if you want e to the power of minus I theta, then we are going to get cos theta minus I sin theta. So if you want cos theta, just add these two things, then we are going to get e to the power of I theta plus e to the power of minus I theta by 2. Right? So in place of theta, substitute omega naught t. So in place of theta, substitute omega naught t. Therefore we are going to get cos omega naught t is equal to e to the power of I omega naught t plus e to the power of minus I omega naught t by 2. So you know basically for e to the power of I theta, you know what's the Fourier transform, and e to the power of minus I theta also, you know, just substitute the Fourier transform and if you simplify, finally we are going to get pi into delta of omega minus omega naught plus delta into pi omega plus omega naught. So this is the thing you have to remember. Sin of omega naught means sin omega t is nothing but from this we can get the value of sin theta. So what is sin theta? So let's do the subtraction of 1 minus 2. Then we are going to get e to the power of I theta minus e to the power of minus I theta by 2j. So if you simplify this value, then inverse of theta substitute omega naught t, and if you simplify, we are going to get the Fourier transform, which is pi by j into delta of omega minus omega naught minus delta of omega plus omega naught. So these things always you have to remember. So listen carefully. Delta of t, the Fourier transform is 1, and for a the Fourier transform is 2 pi into 2 pi a into delta of omega, and for e to the power of j omega naught t, the Fourier transform is 2 pi into delta of omega minus omega naught. So I want you to remember this Fourier transform, this one. If you know this one in this equation, then you can get this cos omega naught t and sin omega naught. You can get with the help of these equations in a very simple format. So I want you to remember only this one, this one. So if you remember this one, then you can get these values very easily. So here, suppose if you remember this one, then here a plus y minus, and here keep j extra downward. So here b plus y minus and keep j extra downward. Then you are going to get this one. So this is what I am trying to tell you. So b plus y minus and keep your extra j down. Then you are going to get this sin omega naught t in case if you forgot this one. So this is what I am trying to tell you. So these things always you have to keep in mind. So for delta of t, the Fourier transform is 1, and for a, the Fourier transform is 2 pi a delta of omega, and for e to the power of j omega naught, the Fourier transform is 2 pi into delta of omega minus omega naught, and for cos omega naught, the Fourier transform is pi into delta of omega minus omega naught plus delta into omega plus omega naught. For sin omega naught, the Fourier transform is b plus by minus and k by divided by j. So this is what we are going to get. So now for the other signal, it is a impulse train. It's basically impulse train. Sigma k is equal to minus n to plus n for delta of t minus kt. So you can see it's a periodic signal. It's a periodic signal of time period t. It's a pulse of train. Where omega naught is equal to 2 pi by t. It's Fourier transform. It is basically periodic signal, right? So for this periodic signal, we are going to figure out the Fourier transform, which is omega naught into sigma k is equal to minus n to plus n to t delta of omega minus k omega naught. So here what I have did v plus t by omega and capital T by omega naught and remaining everything is same. So you keep your extra omega naught. So omega naught into sigma k is equal to minus 2 plus t. Delta of omega minus k omega naught. But omega naught is equal to 2 pi by t. So this is what I am trying to tell you. So finally I can say sigma k is equal to minus 2 plus t. Delta of t minus kt. The Fourier transform is omega naught into sigma k is equal to minus 2 plus delta of omega minus k omega naught. Where omega naught is equal to 2 pi by t. So we can say basically it's a periodic signal. It's an impulse frame. It's an impulse frame of periodic signal of time by t. So for u of t, what's the Fourier transform? Remember, pi in delta of omega plus 1 by j omega. So this you have to remember. So for u of t, the Fourier transform is Laplace transform is 1 by s. The Laplace transform is 1 by s. 1 by s means if one Fourier transform is replace s by j omega, we are going to get 1 by j omega. But there will be some extra factor also, which is pi in delta of omega. So this one you have to remember. This one you have to remember. Then for t to the power of n into t to the power of minus 80 into u of t. So you know the Laplace transform. So what is the Laplace transform? You know for t to the power of n, what is the Laplace transform? N factorial by s to the power of n plus 1. And e to the power of minus 18 is n plus s by s plus a. So therefore we are going to get s plus a. So n factorial by s plus a over the power of n plus 1. Here if you want Fourier transform is 3 plus s by j omega. So you are going to get this value. So this is the expression of the Fourier transform for the signal. So t to the power of n, the Laplace transform is n factorial by s to the power of n plus 1. And if you multiply by e to the power of minus 80, then t plus s by s plus a. So we are going to get n factorial by s plus a over the power of n plus 1. Here if you want the Fourier transform is 3 plus s by j omega, then we are going to get n factorial by e plus j omega on the power of n plus 1. Then e to the power of minus pi t square, the Fourier transform is e to the power of minus pi t square, the Fourier transform is e to the power of minus omega square by 4 pi. And omega is equal to 2 pi f. So 2 pi f, and if you simplify, we are going to get finally. So we are going to get e to the power of minus pi square. Minus pi square because omega is equal to 2 pi f. If substitute simplify, we are going to get this value. Similarly, e to the power of minus a t square, e to the power of minus a t square, the Fourier transform is under root over pi by a into e to the power of minus omega square by 4a. So these things we have to remember. We have to remember because in examinations they will ask you from this concept. So you have to remember. So e to the power of minus pi t square, the Fourier transform is e to the power of minus omega square by 4 pi. So replace omega by 2f, we are going to get this expression. And e to the power of minus a t square, the Fourier transform is under root over pi by a e to the power of minus omega square by 4a. See, I want you to remember this expression, which is this general expression. If you remember this general expression, in place of a, if you substitute pi, then what you are going to get? This value, right? So you are going to get in place of a, if you substitute pi, then you are going to get this expression because pi by cancel here. Here 4 pi you are going to get. So this is what I want you to remember this value, so you can get these things. Then 1 by a plus gt, the Fourier transform is 2 pi into e to the power of a omega into u of minus omega. And 1 by pi t, the Fourier transform is minus j signum of omega. So these things you have to remember. Anyhow, I will give the proof. Already I given the proof for all these things in the classes. But until now, you have to remember. See, basically, this is very simple. See, in place of omega, I have substituted here t. Here what you have to do, you have to multiply by 2 pi extra. In place of t, substitute omega. That's it. So listen carefully. So here in place of omega, I have substitute t. So here in place of t, substitute minus omega. In place of t, substitute minus omega and multiply by 2 pi. So this is the relation, right? So this is the relation. So remember the relation. Remember the formula. So remember the formula. Suppose if f of t has the Fourier transform f of omega. So what is the dual? Dual means the reverse value. So for f of t, the Fourier transform will be 2 pi into f of minus omega. So this I have already told you. So therefore, for f of t, the Fourier transform is f of omega. So f of omega t is in place of omega substitute t. Then its Fourier transform will be 2 pi into f of in place of t substitute minus omega. So this is the property, one of the property here. So for f of t, the Fourier transform is f of omega. So for f of t, the Fourier transform is 2 pi into f of minus omega. So this is what I am trying to tell you. So in place of omega, I have substitute t. Here in place of t, substitute minus omega and multiply by 2 pi. Then you are going to get this one. And 1 by pi t. So 1 by pi t as a Fourier transform minus j signum of omega minus j signum of omega. So these things you have to remember. So finally these things always you have to remember. So finally I can say, remember clearly, e to the power of minus at into u of t as a Fourier transform 1 by a plus j omega. So if you are replacing t by minus t, then replace omega by minus omega. Therefore you are going to get e to the power of at into u of minus t as a Fourier transform 1 by a minus j omega. So do the addition of these two signals, then we are going to get the addition of these two Fourier transforms, we are going to get these things. Simply we can write like this, e to the power of minus a mod t. For t greater than 0, mod t is nothing but plus t, and for t less than 0, mod t is nothing but minus t. So this I have already told you. So do the subtraction of these two signals, then we are going to get the subtraction of these two signals. So we are going to get the corresponding result. Subtraction of these two signals, we are going to get this value, and subtraction of these two signals transforms, we are going to get these things. So in place of a, substitute 0, then we are going to get this value. It is nothing but signum of t. So in place of a, substitute 0, so you also substitute. In place of a, substitute 0, then you are going to get these things. So if you remember this only one, then you can get second one, third one, fourth one, fifth one. Easily you can get. Then for delta of t, you have to remember the Laplace transform of the Fourier transform, this value is at 1. And for a, the Fourier transform is 2 pi into 2 pi a into delta of omega, 2 pi a into delta of omega. So for a, the Fourier transform is 2 pi a into delta of omega. And for e to the power of j omega naught t, the Fourier transform is 2 pi into delta of omega minus omega naught. Then what is cos omega naught t Fourier transform? So if you remember this value, you can get these two things with the help of formula. E to the power of I theta is equal to cos t plus I sin theta. E to the power of minus I theta is equal to cos t minus I sin theta. So in addition of these two signals, we are going to get cos t is equal to e to the power of I theta plus e to the power of minus I theta by 2. And the subtraction of these two signals, we are going to get sin theta is equal to e to the power of I theta minus e to the power of minus I theta by 2j. So in place of theta, substitute omega naught t. And if you simplify, we are going to get finally for cos omega naught t pi into delta of omega minus omega naught plus pi into delta plus omega delta pi into delta into pi omega plus omega naught. So if you want sin omega naught means here v plus by minus, and here keep on next to divide by j. That's it. We are going to get these things. And here it is a periodic signal. It's an impulse train of periodic signal having time period t. Sigma k is equal to minus m to plus m to delta of t minus kt, where omega naught is equal to 2 pi by t. It has a Fourier transform omega naught into sigma k is equal to minus m to plus m to delta of omega minus k omega naught. And for u of t, the Fourier transform is pi into delta of omega plus 1 by j omega. So Laplace transform is 1 by s. Laplace transform is 1 by s. Fourier transform is replace s by j omega and keep an extra factor pi into delta of omega. Pi into delta of omega. And you know, e to the power of n into e to the power of minus 8 into u of t, you know the Laplace transform, which is n factorial by s plus a all the power of n plus 1. If you want Fourier transform is a plus s by j omega, we are going to get these things. And I want to remember this one. For e to the power of minus 8 t square, the Fourier transform is under root over pi by a into e to the power of minus omega square by 4a. E to the power of minus 8 t square, e to the power of minus 8 t square, the Fourier transform is under root over pi by a into e to the power of minus omega square by 4a. So this one you have to remember. Suppose in place of a, if substitute pi, then here in place of a substitute pi, we are going to get this thing. And omega is equal to 2 pi. For the simplify, we are going to get this value. And I already told you, for f of t, the Fourier transform is f of omega, and for f of a, the Fourier transform is 1 by mod a, f of omega by a can be positive or negative. And capital F of t as a Fourier transform 2 pi into small f of minus omega. So here I have replaced omega by t. So here replace t by minus omega and multiply by 2 pi. So we are going to get these things. And 1 by pi t, we have to remember the Fourier transform is minus j signum of omega. So these things always you have to keep in mind. So finally, here let me write some important formulas so that you can easily able to understand. Only I want to remember only these Fourier transform formulas only. I want you to remember e to the power of minus at into u of t. So for this, what is the Fourier transform? 1 by v plus j omega. So now the next important formula that I want you to remember, which is for delta of t, the Fourier transform is 1. The Fourier transform is 1. And for A, the Fourier transform is 2 pi A into delta of omega. And for e to the power of j omega naught t, the Fourier transform is 2 pi into delta of omega minus omega naught. And another important formula that I want you to remember is sigma k is equal to minus infinity to plus infinity delta of t minus kt. Here omega naught I am going to assume 2 pi by t. For this, the Fourier transform is omega naught into sigma k is equal to minus infinity to plus infinity delta of omega minus k omega naught. So, and finally, here I am writing the formula, important Fourier transform formula, which is u of t. So, for u of t, the Fourier transform is pi into delta of omega plus 1 by j omega. And one more important formula, e to the power of minus a t square, for which the Fourier transform is under root over pi by a into e to the power of minus omega square by 4a. And 1 by pi t as the Fourier transform minus j sigma of omega. And finally, suppose for f of t, if the Fourier transform is f of omega, then for f of at, the Fourier transform is 1 by mod a, f of capital F of omega by a. Here a can be positive or a can be negative. Capital F of t is nothing but it is Fourier transform is 2 pi into small f of minus omega. Here, in place of omega, I have replaced p here. In place of t, replace minus omega, I multiply by 2 pi. So this is I want you to remember only these things. If you remember these things, you can get the other things in a very simple manner. So for e to the power of minus at into u of t, the Fourier transform is 1 by a plus j omega. And for delta of t, the Fourier transform is 1. And for e, the Fourier transform is 2 pi a in the delta of omega. And for e to the power of j omega naught, the Fourier transform is 2 pi in delta of omega minus omega naught. And for sigma k is equal to minus infinity delta of t minus kt, where omega is equal to 2 pi by t as a Fourier transform omega naught into sigma k is equal to minus infinity delta of omega minus k omega naught. And for u of t, the Fourier transform is pi in delta of omega plus 1 by j omega. And for e to the power of minus a t square, the Fourier transform is r root over pi by a, e to the power of minus omega square by 4a. And for 1 by pi t, the Fourier transform is minus j sigma of omega. And for f of t, the Fourier transform is f of omega. For f of at, the Fourier transform is 1 by mod a, f of omega by a. And for capital F of t, as a Fourier transform 2 pi into small f of minus omega. And one more important formula, which is, you have to remember, e to the power of I theta is equal to cos theta plus I sin theta. And e to the power of minus I theta is equal to cos theta minus I sin theta. So what is cos theta? Cos theta is equal to e to the power of I theta plus e to the power of minus I theta by 2. And sin theta is equal to e to the power of I theta minus e to the power of minus sin theta by 2j. So these things always you have to keep in mind. So if you remember all these formulas, then you can solve a majority of the questions in the Fourier transform. So this is what I am trying to tell you. Now we are going to discuss about the some important point, which is the first one, which is nothing but f of omega is well defined for all omega. So f of omega is well defined for all omega as omega lies from minus m to plus infinity. So because these signals in time domain are absolutely integrable, so we can say these are energy signals. See, for the first one, f of omega is well defined for all omega, for omega lies from minus m to plus infinity, because these signals in time domain are absolutely integrable, which are energy signals. So if you see clearly here basically for some Fourier transforms I have mentioned 1, 1, 1, 1, 2, 2, 2, 2, 2, 2. So here 2 I have mentioned. So what is the meaning of these things I am going to tell you here. Listen carefully. Suppose the first thing is here I am going to discuss about the 1. So wherever I have given 1, I will discuss those things in a very detailed manner. So if you see clearly, e to the power of minus AD into u of t, I've already told you, this is a decreasing exponential. So therefore, we are going to get a finite energy. Energy is equal to integration from t is equal to minus n to plus n t, f of t whole square dt. So if we try to figure out the energy for the signal, we are going to get a finite energy. So therefore, this is called as the energy signal. And this is also nothing but if you try to find energy under the signal waveform, so this is also going to give you finite. This is also going to give finite value. So this is also energy signal. So for this one also, so whichever one, so this signal, so this signal, so these four signals are nothing but these are basically all as this first, second, third, fourth. So these are nothing but these are the finite energy signals, or they have the finite energy. So therefore we can say these are the energy signals, because the energy is equal to energy in a signal f of t is equal to integration from t is equal to minus 1 to plus infinity mod of f of t whole square dt. So if we figure out this area, so if we figure out the energy, we are going to get the finite energy. So therefore we can say these are the energy signals. So for energy signals, if you try to figure out the Fourier transform, we are going to get certain expression, and this is defined for all omega. So it is defined for all and every omega. So for each and every omega, you are going to get some value. So we can say this well defined. So if omega is well defined for all omega, so we can say when a signal is an energy signal, so if you try to find the Fourier transform for energy signals, then f of omega is defined for all values of the omega. So listen carefully. If a signal that you are going to consider is an energy signal, and if you try to find the Fourier transform for that energy signal, then we are going to get the value when we are going to get the f of omega, which is well defined, means it is defined for each and every value of the omega. So now what is the next point, which is 2. Here f of omega is not well defined for some omega in omega plus or minus 70 because these signals in time domain are not absolutely incredible, means they are called as the power signals or not energy signals. So what I am trying to tell you is very simple. Now let's go for the second thing. What is the meaning of this second thing? These are not energy signals. These are not energy signals. If these are not energy signals, or we can say these are the power signals. If they are not energy signals, means they will be power signals. So listen carefully, if these are not energy signals, then definitely the Fourier transform is not defined at each and every point, means at certain points, the Fourier transform is not well defined. So if you see clearly, here minus 2 j by omega, here minus 2 j by omega. So at omega is equal to 0, we are going to get infinity, right? So it is not defined at omega is equal to 0. Similarly, here also, delta of t is nothing but it is basically, we can say that, so delta of t is nothing but it is having a area is equal to 1 and t is equal to 0. So therefore, here we can say that this is also is not an energy signal. So therefore, this you are going to get Fourier transform as 1. Whereas the remaining, so this A is also not an energy signal. So you can see 2 pi in delta of 2 pi A in delta of omega. So all these are called as the non-energy signals. If they are not energy signal, means the Fourier transform at certain points, it is not perfectly defined. It is not perfectly defined. So f omega is not well defined for some omega. So what I am trying to tell you is very simple. Listen carefully. So listen carefully. Here I am going to tell you some important point. Suppose if f of t is an energy signal, then the Fourier transform is defined for each and every value of omega. Suppose if it is not an energy signal, then f of omega is not defined at certain values of omega. At certain values of omega, it is not defined. But even though you are going to get the Fourier transform expression, but at certain values of omega, it is not going to get defined. So this is what I am trying to tell you. So therefore, we can say if the signals are the energy signals, and if you try to find the Fourier transform for these energy signals, then we are going to get the Fourier transform. It is defined for each and every value of omega. But if you take a signal which is not an energy signal, and you can even find the Fourier transform also, but if you find the Fourier transform at certain points, it is not well defined. So we can say it is well defined. We can say this is well defined, means at each and every value of omega, it is perfectly defined. Not well defined means at certain values of omega, it is not well defined. It is not defined at certain values of omega. So this is what I am trying to tell you. So finally, I can say, if you are taking an energy signal, suppose if you are going to take an energy signal, then the Fourier transform is defined at each and every value of omega. If the signal is not an energy signal, then the Fourier transform is not defined at certain values of omega. So this is what I am trying to tell you. So here you can see this is energy signal, energy signal, energy signal, energy signal, energy signal. So this is also energy signal. So after this energy signal, the Fourier transform is defined at each and every value of omega. We define at each and every value of omega means we are going to get some finite value for each and every omega. So if it is not an energy signal at certain values of omega, it is not defined means you are going to get infinity. Not defined means you are going to get infinity. So that is the meaning of this one. So finally, I can say whenever you are going to consider an energy signal as f of t, and if you try to find the Fourier transform, then it is we are going to get certain expression. It is defined at each and every value of omega. But if you are taking f of t as a non-energy signal, it is not an energy signal, then the Fourier transform is not defined at certain values of omega. So finally, I can say simply I can say like this: if you are taking f of t as energy signals, then the Fourier transform is defined at each and every value of omega. If the signal f of t is not an energy signal, then at certain values of omega, the Fourier transform is not defined. So this is what I am trying to tell you finally. So finally I can say, if the signal that you are going to consider is an energy signal, then the Fourier transform is defined. Means it is defined at each and every value of omega. If you are taking the signal f of t as it is not an energy signal, then it is not defined at certain values of omega. Not defined means infinity. Defined means it is a finite value for each and every value of omega. So listen carefully. First signals means f of omega is well defined for all omega. For omega lies from innocent to infinity, because these signals in time domain are absolutely integrable, or we can say these are the energy signals. So the second thing is, here f of omega is not well defined for some values of omega. In omega lies from innocent to infinity, because these signals in time domain are not absolutely integrable. Means you can say these are not energy signals or power signals. So you can say. So finally, I can say only one thing. Suppose if the f of t, if you are taking an energy signal means it is absolutely integrable, then the Fourier transform is well defined for each and every value of omega. Means you are going to get a finite value. Suppose if you are taking f of t, which is a power signal or not an energy signal, means it is not absolutely integrable, then we can say the Fourier transform, it is not defined at certain values of omega. Not defined means you are going to get the infinity value. So these things always you have to keep in your mind. Now we are going to discuss another concept which is called as the Fourier transform properties. So we are going to discuss the Fourier transform properties in a very detailed manner. The first property is a time shifting property that we are going to discuss, which is, so for f of t, the Fourier transform is f of omega. So f of omega means it's a complex number, so I can write in the magnitude as well as a phase angle. So I can write like this, which is mod of f of omega or into e to the power of j of phase angle of f of omega. Or simply we can say, you can also write like this, mod of f of omega, phase angle of f of omega. You can write like that, or either you can write like this. See what I told you. You can write like either r into e to the power of I theta, you can write, or you can also write r angle theta. You can write in any other fashion. So we can say f of omega is equal to mod of f of omega and a phase angle of f of omega, or mod of f of omega into e to the power of I into angle of f of omega. You can write like any other thing. So for f of t plus t naught, the Fourier transform is f of omega into e to the power of j omega t naught. So if you write in the matter format, it will become mod of f of omega into e to the power of j of phase angle of f of omega plus omega t naught plus omega t naught. Here it is basically the phase angle. It is a phase angle of f of omega plus omega naught. Then here, which is simply we can say that suppose if f of t minus t naught is there, then the Fourier transform is f of omega into e to the power of minus j omega t naught, or the amount of f of omega into e to the power of j of the phase angle of f of omega minus omega t naught. So here plus means here plus, here also plus. The minus means here minus, here also minus. So in the shortcut, what we can say, in the shortcut, and I can write like this generally. So for f t plus or minus t naught, what is the Fourier transform, which is equal to, the Fourier transform is e to the power of j plus or minus omega t naught into f of omega. So this is what I am trying to tell you. So you can see for f of t plus or t, or f of t plus or minus t naught, the phase angle is e to the power of, the Fourier transform is e to the power of plus or minus j omega t naught into f of omega. So you can, if you want to write in the other format, which is, you can write like this: mod of f of omega at a phase angle of, you can say f of omega is a phase angle of f of omega plus or minus omega t naught. So these two things. So here you can write the phase angle of f of omega. So plus or minus omega t naught. So these things always you have to keep in your mind. So here the magic part, we have the phase angle part. So you can see for f of t plus or minus t naught, what is the Fourier transform e to the power of plus or minus j omega t naught f of omega. I think you have remember this formula in the case of Laplace transform. For f of t minus a, what is the Laplace transform? The Laplace transform is e to the power of minus as into f of s, right? I think you have remembered. So this is a Laplace transform formula. But if you want the Fourier transform is, here replace s by j omega, we are going to get minus a j omega. Here f of omega you can write like this. So same thing, right? Here also same thing. Here replace a by t. Here replace a by t naught. Here what we are going to get e to the power of minus j omega t naught f of omega, right? Same thing. Here also same thing, right? Same thing, right? Here also same thing. So what is the general formula? Here minus, here minus. Suppose here it is a plus means here also plus. Here also plus. So if you remember the this Laplace transform formula, then we can easily get the Fourier transform formula just by transforming s is equal to j omega. So this is I can say. So therefore, if you remember this Laplace transform formula, which is for f of t minus a, the Laplace transform is e to the power of minus a s into f of s. If you want Fourier transform is replace s by j omega, you are going to get e to the power of minus j a omega f of omega. So here you replace a by t naught, then we are going to get, which is e to the power of minus j omega t naught f of omega. So plus means plus, minus means minus. So therefore we can say, for simply we can say like this. So finally we are going to get like this, which is f of t plus or minus t naught as the Fourier transform e to the power of plus or minus j omega t naught f of omega. So you can write in a other format, which is mod of f of omega phase angle of, at a phase angle of f of omega plus or minus omega t naught. So therefore, if you remember this Laplace transform formula, then we can easily get the Fourier transform formula just by replacing s is equal to j omega. So this is what I am trying to tell you, right? So this is an easy thing. Now let's go for the other thing, which is for delta of t, the Fourier transform is 1. Just now we have discussed, right? So for delta of t, what is the Fourier transform? 1. For delta of t plus t naught, I have already told you what is the Laplace transform, what is the Fourier transform. By using this formula, e to the power of j omega t naught into previous Fourier transform, which is equal to 1 into 1, which is nothing but this one. Delta of t minus t naught is nothing but e to the power of minus j omega t naught into Fourier transform of delta of t, which is nothing but 1. So therefore we can say delta of t plus t naught is equal to e to the power of plus j omega t naught, and delta of t minus t naught is nothing but it is equal to e to the power of minus j omega t naught. So if you remember this formula, so always have to remember this formula. For f of t, the Fourier transform is f of omega. Then for f of t plus or minus t naught, the Fourier transform is e to the power of plus or minus j omega t naught f of omega. So by using this property, we got this one. So for delta of t, the Fourier transform is 1. For delta of t plus t naught, the Fourier transform is e to the power of plus j omega t naught. Whereas for delta of t minus t naught, the Fourier transform is e to the power of minus j omega t naught. C into the Fourier transform of delta of t, which is nothing but 1. So this is the thing always you have to keep in your mind. Suppose if I add these two things, what I am going to get? So if we add these two things, then we have to add these two things also. If the rest are added means the rest are also added. So if you have the RHS, then for finally you are going to get 2 cos omega t naught, because you know e to the power of phi theta is equal to cos theta plus sin theta. E to the power of minus sin theta is equal to cos theta minus sin theta. So from this if we add, we are going to get finally 2 cos theta. Cos theta is equal to omega t naught. So 2 cos omega t naught. Similarly, if you subtract these two things, then what you are going to get? You have to subtract these two things also. If you subtract, we are going to get 2j sin theta. It is nothing but omega t naught. So from this, we can get the value of cos omega t naught. Cos omega t naught is equal to here we can say, so therefore we can say delta of t plus t naught plus delta of t minus t naught as a Fourier transform cos omega t naught, and delta of t plus t naught minus delta of t minus t naught as a Fourier transform 2j sin omega t naught. So this is what I'm trying to tell you. So these things I want to keep in your mind. So therefore, what is the general formula I want to tell you? So general formula. So what is the general formula? As I already told you, here f of t plus t naught plus f of t minus t naught. If you add these two things, I have to add the RHS also. If I add the LHS means I have to add the RHS. So if you simplify, what you are going to get 2 into f of omega into cos of omega t naught. Suppose if you subtract these two things, and then you have to subtract these two things also. So if you simplify, we are going to get 2 into j f of omega sin omega t naught. So these things always you have to keep in your mind. So these things always you have to keep in your mind. So let me write here finally. So let me write here finally. See some important properties here. Let me write here so that we can be able to remember for lifetime for so much amount of time. So here, see, you can listen carefully. So for f of t, if the Fourier transform is f of omega, then I have already told you for f of t plus or minus t naught. What is the Fourier transform? I have already told you with the power of plus or minus j omega t naught f of omega, right? So now, what is the another thing here? If you go for this one, f of t plus t naught plus f of t minus t naught, then what do you get here? 2 into f of omega into cos omega t naught we are going to get. Subtract. We subtract what we are going to get? t plus t naught minus f of t minus t naught. T minus t naught. So t minus t naught. Then we are going to get 2 into 2j into f of omega into sin omega t naught. So this is what I am trying to tell you. So this thing you have to remember. So now, so if you remember one thing, you can easily get the other two. So these things always you have to keep in mind. Right? So these four formulas. So this formula, and this one and this one. You have to keep in your mind. Now let's go for the time scaling. So previously we have learned the time shifting. Time shifting means whether you are delaying the signal or either you are advancing the signal. So now here time scaling. Basically we have time scaling. Time scaling means whether we can address the signal or either we can expand the signal. Time scaling is that property. So for f of t, the Fourier transform is f of omega, then f of at has the Fourier transform already told you 1 by mod a, f of omega by a, where a can be positive or negative. Suppose f of t by a, f of t by a means reverse replace of a, substitute 1 by a, then what you are going to get? Replace of a, substitute 1 by a, then we are going to get mod a into f of omega by, replace of a, substitute 1 by a, we are going to get a into omega. So I want you to remember only this one. If you remember this one, a can be positive or a can be negative, a can be greater than 0 or a can be less than 0. It can be anything, right? We can substitute any value of a, that is a positive, it is a negative, anything we can substitute. So if you remember this one, you don't have to remember this one. Then what is going to happen? Suppose for this one, so here divide by 1 by mod a on both sides, then what you are going to get? 1 by mod a, f of t by a is nothing but f of a omega, right? A can be positive or negative. So I want you to remember only these things. So because a can be greater than 0, a can be less than 0, a can be positive or a can be negative. So if you remember this one, you don't have to remember this other thing. So therefore, for f of t, if the Fourier transform is f of omega, then f of at has the Fourier transform 1 by mod a, f of omega by a, f of omega by a. Then a can be positive or a can be negative. A can be positive or a can be negative. So this is the, generally, we are going to this expression from this section only. We are replacing a by 1 by a, then we are going to get this value. If we replace a by 1 by a, then we are going to get mod a. If we replace a by 1 by a, we are going to get a into omega. Here, this mod a I have taken here. So it will become 1 by mod a, f of t by a is equal to f of a omega. So this is what I am trying to tell you. Here also same thing. Here also is positive, is also negative. In this case also same thing. Condition is a can be positive, a can be negative. So I want you to remember only one thing. So here let me write here. So this is one more important part. Here this is a time shifting property, this is a time scaling property. So for f of t, the Fourier transform is f of omega, then f of at as the Fourier transform is equal to 1 by mod a into f of omega by a. Here a can be positive, a can be negative. It can be any value. It can be either a can be greater than 1 or less than 1 also we can say. A can be greater than 1 or less than 1. Greater than 1 means it is playing a signal. Lesser than 1 means it is expanding the signal. So if you remember this one, we don't have to remember any other thing. Suppose if we multiply mod a on the both sides, then we can also write like this. Mod a into f of vat is nothing but f of omega by a. Right? We can even get like this. Again, same thing. A can be positive, A can be negative. This will be the same thing. I'm multiplying mod on the both sides, then I got this expression. So this is the time scaling property. If a is greater than 1 means it is producing the signal. If a is less than 1 means it is expanding the signal. So these things always you have to keep in your mind. So now let's go for the frequency shifting. Frequency shifting means in the frequency we are doing the shifting. Then what is going to happen in the time domain that we are going to see. So frequency shifting. So f of t has a Fourier transform f of omega. Suppose we are delaying the signal in the frequency domain f of omega minus omega naught. Then what is the thing in the time domain which is f of t into the power of j omega or omega naught t. Suppose if we are advancing the signal in the frequency domain, then what is the expression in the time domain which is f of t into e to the power of minus j omega naught t. So these things always you have to keep in your mind. So here let me write here so that you can easily able to understand in a shortcut manner. So frequency shifting. So here f of t has a Fourier transform f of omega. So f of t has a Fourier transform f of omega. And if you are basically doing the frequency shifting means either in the frequency domain, the signal can be either delay or either it can be advanced. So let me write the general expression. Okay, so f of omega plus or minus omega naught. Then what is the time domain expression? Let me write here. So here e to the power of here plus minus means minus means reverse. Reverse you have to write. There is a reason I have taken minus and plus. Then j omega naught t into f of t. So this is what we have to remember. Here plus means here minus. Here minus means here plus. So f of t as a Fourier transform f of omega. For f of omega plus or minus omega naught, the Fourier transform is e to the power of minus or plus j omega naught t f of t. So this is what always you have to keep in your mind. Here plus means here minus. Here minus means here plus. So this is what I am trying to tell you. So therefore, you can say for f of t as a Fourier transform f of omega, for e to the power of minus plus j omega naught t, f of t as a Fourier transform f of omega plus or minus omega naught. Here minus means here plus, here plus means here minus. So this you can easily get with the help of expression also. But Fourier said the Fourier transform expression also, we can directly get from the expression. Even if you forgot, we can get directly from the expression also. So this is what I am trying to tell you. This is a frequency shifting. Now go for the modulation theorem. So modulation theorem we are going to study. What is the modulation theorem? So f of t into cos omega naught t. So f of t into cos omega naught t as a Fourier transform. So this one just now we have discussed, right? So let me see here. So here f of t into cos omega naught t. So f of t into cos omega naught t. So basically here you see here cos omega naught t. So cos omega naught t, how you can write cos omega naught t. I have already told you e to the power of I omega naught t plus e to the power of minus I omega naught t by 2. You can write like this and multiply by f of 2 there. And if you apply the Fourier transform, finally we are going to get half into f of omega minus omega naught plus f of omega plus omega naught. Then f of t into sin omega naught t. What's the Fourier transform? Sin omega naught t, how you can write e to the power of I omega naught t minus e to the power of minus I omega naught t by 2j. So if you multiply and if you simplify and then if you apply the Fourier transform, we are going to get 1 by 2j f of omega minus omega naught plus f of omega plus minus of f of omega minus omega naught. There plus means it will be a minus. Here 1 by 2 means there will be 1 by 2j. So this is the thing always you have to keep in mind. So let me write here. So let me write the formula, the modulation formula. Let me write here. So for f of t into cos omega naught t. So f of t into cos omega naught t as a Fourier transform, which is nothing but 1 by 2 into f of omega minus omega naught plus f of omega plus omega naught. So this is the point we have to remember. And for f of t into sine omega naught t as a Fourier transform. Here there will be 1 by 2j into f of omega minus omega naught minus f of omega plus omega naught. So these things always you have to keep in mind. So this is the modulation principle. Even if you forgot also, you can easily get a plus cos omega naught t by e to the power of I omega naught t plus e to the power of minus I omega naught t by 2. And if you apply, then if you apply Fourier transform, you are going to get this one with the help of this basic formula, right? You have to apply this Fourier transform, you have to get this value. Similarly, sin omega naught t nothing but e to the power of I omega naught t minus e to the power of minus I omega naught t by 2j. And then multiply and apply this property, then you are going to get this value. So these things always you have to keep in your mind. So now the next property is the area of the signal. The area of the signal under the f of omega. So basically for f of t, we have figured out the f of omega, and we want to find what is the area under the f of omega. We want to figure out how to do that one. Let me see here. Suppose for f of t, you know the Fourier transform f of omega. So I've already told you how to write the f of t from f of omega. This one I've already told you. Let me write here. Let me type here. So f of omega is equal to integration from t is equal to minus infinity to plus infinity f of t into e to the power of minus j omega t into dt. I've already told you. Suppose this from f of t we got the f of omega, but if you want the reverse f of t, then I've already told you we have to go from omega is equal to minus infinity plus infinity f of omega e to the power of minus plus j omega t into d omega. We are doing with respect to omega. So there will be extra factor of 1 by 2 pi. So this one I already told you so many number of times. So f of t is equal to 1 by 2 pi integration from omega is equal to minus infinity plus infinity f of omega e to the power of j omega t d2. So now I will multiply 2 from both sides. Then basically here, see, in place of t and substitute 0. In place of t and substitute 0. Then what I am going to get? F of 0 is equal to 1 by 2 pi integration of omega is equal to minus infinity plus infinity f of omega. This should become 1 into d omega. And I will multiply 2 pi on both sides. Then I am going to get 2 pi into f of 0 is equal to integration from omega is equal to minus infinity plus infinity f of omega d omega. So this is nothing but area under the f of omega, area under the f of omega. So integration of omega is equal to minus infinity plus infinity f of omega d omega is equal to 2 pi into f of 0. So therefore, if you want to know what is the area under the f of omega, then just try to find 2 pi into f of 0. F of 0 means for the signal f of t and t is equal to 0, what is the value? Just figure out and multiply by 2 pi, then you are going to get the area under the f of omega. So always remember, if you know f of t, then you can get the f of omega is equal to integration from t is equal to minus infinity plus infinity f of t into the power of minus j omega t into dt. But if you know f of omega, if you want f of t, then f of t is equal to 1 by 2 pi integration from omega is equal to minus infinity plus infinity f of omega and minus means here plus e to the power of j omega t into d omega. So this is the expression I've taken. Here t is equal to 0, I have substitute. So this value will become 1 and I multiply by 2 pi on both sides. Then I am going to get finally, which is integration from omega is equal to minus infinity plus infinity f of omega d omega is equal to 2 pi into f of 0. Means at t is equal to 0, so try to find what is the signal value for f of t and multiply by 2 pi in order to get the area under the signal f of omega. So let me write the formula here. So these things always you have to keep in mind. So integration from omega is equal to minus infinity to omega is equal to plus infinity, capital F of omega d omega is equal to 2 pi into f of 0. So these things always you have to keep in mind. So now let's go for the other property, which is called as the Parseval's theorem. So this is a very, very important theorem. So I recommend you to always keep in mind. So this is called as a Parseval's theorem. Which is, so basically I want to find what is the energy under the signal. So basically, suppose there is a f of t and there is a f of omega. So for f of t, we have figured out the Fourier transform. The energy is same. The energy is same f of t as well as the f of omega. So these two things I want to figure out. So the energy is same in both the f of t as well as the f of omega. So energy of the signal is same in both the f of t as well as the f of omega. And what is the expressions in order to get the energy? Suppose if you know f of t, then how to get the energy? This is the basic thing I already we discussed. E is equal to integration from t is equal to minus infinity to plus infinity mod of f of t whole square dt. So if you know f of t, with the help of this expression, you can figure out the energy and the f of t. So for f of t, we have got the f of omega. Then how to get the energy in terms of f of omega, which is 1 by 2 pi integration from omega is equal to minus infinity to plus infinity mod of f of omega whole square d omega. So now suppose omega is equal to 2 pi f. So omega is equal to 2 pi f, right? So omega is equal to 2 pi f. So d omega is equal to 2 pi into df, 2 pi into df. So if we substitute d omega is equal to 2 pi df, 2 by 2 pi cancels, then we are going to get in terms of df, which is integration of f is equal to minus infinity to plus infinity mod of f of f whole square df. Because if omega is equal to minus infinity, so f is also minus infinity. If omega is equal to plus infinity, f is also equal to plus infinity. Either you can write in terms of omega, or either you can write in terms of f frequency also you can write. See, basically this modulus is nothing but, I'm already telling you, modulus is nothing but it is a magnitude spectrum. Magnitude spectrum is always an even spectrum. So even spectrum means you can write like this. Basically this expression you can also write like this, which is 2 times of, so 1 by 2 pi into 2 times of integration omega is equal to plus infinity mod of f of omega whole square d omega. So 2 cancels, we are going to get finally 1 by pi. So therefore this is what I am trying to tell you. So therefore these are the different ways of expressing the energy. So for a given f of t, signal, we are going to get the Fourier transform f of omega. So for a given f of t signal, we are going to get the Fourier transform f of omega that we are going to get. The energy of the signal in f of t and the energy of the signal for the corresponding f of omega is same. So the expressions are E is equal to integration from t is equal to minus infinity to plus infinity mod of f of t whole square dt, which is equal to 1 by 2 pi integration omega is equal to minus infinity to plus infinity mod of f of omega whole square d omega. So the magnitude of the Fourier transform, or if it's a magnitude spectrum, is always it is an even signal. So because the magnitude spectrum is always an even spectrum, so because of that we can say finally 1 by 2 pi into 2 times of integration from omega is equal to 0 to plus infinity mod of f of omega whole square d omega. So 2 cancels, we are going to get finally 1 by pi integration of omega is equal to 0 to plus infinity mod of f of omega whole square d omega. Suppose if you want to write in terms of frequency, then a plus omega is equal to 2 pi f, so d omega is equal to 2 pi df. So if you substitute and simplify here, then what you are going to get? So 2 by 2 pi cancels in terms of frequency. So integration of if omega is equal to minus infinity, f is equal to minus infinity. If omega is equal to plus infinity, if omega is equal to plus infinity, the frequency is also plus infinity. So integration of f is equal to minus infinity to plus infinity mod of f whole square df. You can write like this, or either you can also write like this. Now we can also write like in another fashion also. In terms of frequency, if you want, then 2 times of integration of f is equal to 0 to f is equal to plus infinity mod of f of f whole square df. You can write like this. So you can write in any of the fashion. And the concept is same. So finally, let me write the expressions here so that you can easily able to understand the partial equations. So let me write here. So therefore, what is our E formula? E is equal to, so E is equal to integration from T is equal to minus infinity to plus infinity mod of f of t whole square into dt. Or we can write 1 by 2 pi integration of omega is equal to minus infinity to plus infinity mod of f of omega whole square d omega. So the magnitude spectrum, mod of f of omega is a even spectrum, it is even spectrum. So the scale is also even spectrum. If there is an even spectrum, the scale is also even spectrum. So because of that, what we are going to get finally 1 by pi integration of omega is equal to 0 to plus infinity mod of f of whole square into d omega. So if you replace omega by 2f, if you replace omega is equal to 2 pi f, then you can get like expressions like this. If omega is equal to 2 pi f, if 2 by 2 pi cancels, we are going to get like this, which is, so we can get like this, omega f is equal to minus infinity to plus infinity mod of f whole square df, or it will be 2 times of integration of f is equal to 0 to infinity mod of f of f whole square df. So these are the different expressions. Or you can write down in terms of omega or in terms of f or in terms of t. These are the different relations. So therefore, E is equal to integration from t is equal to minus m to plus m into mod of f of t whole square dt is equal to 1 by 2 pi. Integration of omega is equal to minus m to plus m into mod of f of omega whole square d omega. So, or it is equal to 1 by pi. Integration of omega is equal to 0 to plus m into mod of f of omega whole square d omega, or integration of f is equal to minus m to plus m into mod of f whole square df, or 2 times of integration of f is equal to 0 to infinity mod of f of whole square df. These are the different relations that we always have to keep in the mind. So now the next property is multiplication. It is a multiplication property. So multiplication by t we are going to discuss. So what happens in the time domain if you multiply by t, then what is happens in the Fourier transform that we are going to study. Which is for f of t, if the Fourier transform is f of omega, then t into f of t has the Fourier transform j into df of omega by d omega. J into d into f of omega by d omega. So this one you have to remember. So for f of t, the Fourier transform is f of omega. For t into f of t, the Fourier transform is j into df of omega by d omega. So this formula we have to remember. So for f of t, the Fourier transform is f of omega. So for t into f of t, the Fourier transform is j into df of omega by d omega. So this is what I am trying to tell you. So therefore, here let me write the property here so that we can easily able to understand. So let me write here. So I can say that so for f of t, the Fourier transform is f of omega. Then for t into f of t, the Fourier transform is j into df of omega by d omega. This is what I am trying to tell you. So this is always you have to keep in mind. The next property is duality. Duality principle that we are going to study. So for f of t, the Fourier transform is f of omega. F of omega, f of f also you can write either you can write omega or anything is the same. Then for capital F of t as the Fourier transform 2 pi into small f of minus omega, or you can write f of minus f, you can write. So this is what I am trying to tell you. So therefore, listen carefully. See, basically, what is the meaning of duality? Suppose for a given f of t, you got the Fourier transform signal. See, in the Fourier transform signal, I want to keep as it is in the time domain. So I want to keep as it is in the time domain. So whatever the frequency domain signal I got, same signal I want to keep in time domain. Then what is the corresponding Fourier transform is 2 pi into small f of minus omega, means replace t by minus omega and multiply by 2 pi. Suppose if you want to write in terms of f means here omega means f, here f of minus omega. Omega is nothing but here basically keep here just f of minus f, you have to keep small f of minus f. Just keep replace omega by minus f, that's it. Replace t by minus f, that's it. F of minus f. So this is in terms of omega, this is in terms of small f, this is in terms of small f. So this is what I am trying to tell you. So this is in terms of small frequency and this is in terms of f. So f of t has a Fourier transform f of omega or f of f. Then f of t has a Fourier transform 2 pi into f of minus omega or f of minus f. So this is what I am trying to tell you. So duality means vice means say for f of t I have to figure out the Fourier transform. So basically now I want to obtain a time signal same as a Fourier transform. What is the Fourier transform? Same signal I want to get in a time domain. Then what is the corresponding Fourier transform I want to figure out? Just 2 pi into f of minus omega or just keep it f of minus f, just keep it here. This is what I am trying to tell you. So let me write here. Duality principle, let me write here so that we can easily able to understand. So what is the duality principle? So for small f of t, if the Fourier transform is f of omega or f of small f, we can write in terms of f, capital omega or f. Then capital omega, then f of t as a Fourier transform, just 2 pi into f of minus omega or f of minus f, that's it. So this is what I am trying to tell you. So therefore, f of t as a Fourier transform f of omega or f of f, and capital F of t as a Fourier transform 2 pi into f of minus omega, means replace f t by minus omega and multiply by 2 pi, or just keep f of minus f. In terms of frequency means replace t by minus f. So these are the two expressions that you always have to keep in the mind. So this is called as the duality. Now, area of the signal f of t. So basically, previously we have known about the how to figure out the area under the f of omega. But now we have to find what is the area of the signal f of t. Means what is the area under the signal f of t I want to figure out. So what is the thing that we have to do? Which is for f of t, if the Fourier transform is f of omega, then you know the basic formula f of omega is equal to integration from t is equal to minus f to plus root f of t into e to the power of minus j omega t dt. So now here in place of omega I want to substitute 0. Then what I am going to get? In place of omega if you substitute 0, then you are going to get this value 1. So f of 0 is equal to integration from t is equal to minus f to plus root f of t dt. So this is nothing but area under the signal f of t is equal to f of 0. So in place of omega for f of omega, c at omega is equal to 0, what is the value? And that's it, that is called as the area under the signal f of t. So for f of t, the Fourier transform is f of omega. The expression is f of omega is equal to integration from t is equal to minus f to plus root f of t into e to the power of minus j omega t dt. So in place of omega as up to 0, then this value will become 1. So we are going to get f of 0 is equal to integration from t is equal to minus f to plus root f of t dt. So this is nothing but area under the signal f of t is equal to capital F of 0. Means for the Fourier transform, try to see at omega is equal to 0, what is the expression? That is nothing but, so what is the value that you have to figure out? That is nothing but simply the area under the signal f of t. So let me write the expression. So therefore, integration from t is equal to minus infinity to plus infinity f of t to dt. It is nothing but capital F of 0. So this one always you have to keep in your mind. So now let's go for the other property, which is the convolution property. So we are going to discuss the convolution property. So what is the meaning of convolution property? This one I wanted to convolution is simply we can say in the time domain the two signals are convoluted, then what is going to happen in the frequency domain that we are going to study. Suppose for f of t, the Fourier transform is f of omega, and for h of t, the Fourier transform is h of omega, and y of t is nothing but f of t convolution of h of t. So for y of t, what is the Fourier transform? Y of omega is equal to f of omega into h of omega. So this important statement I want to prove this so many number of times. So the conversion time domain, which will become multiplication in the Fourier frequency domain. So therefore we can say the multiplication in the time domain, it will become the convolution of the time domain, it will become multiplication in the Fourier transform domain. So this is not always you have to keep in your mind. So therefore we can say the convolution of the time domain, it will become multiplication in the frequency domain. So for f of t, the Fourier transform is f of omega. For h of t, if the Fourier transform is h of omega, then y of t is nothing but f of t convolution of h of t. If there is Fourier transform, y of omega is equal to the f of omega into h of omega. So therefore, the convolution time domain will become multiplication of the frequency domain. Suppose, let me give you the meaning of this one. Suppose if you take an LTI system, for LTI system, the impulse response is h of t and the input is f of t. Then what is the output? So the output is something like y of t. So you know y of t is something like y of t is a convolution of the input as well as the impulse response. So f of t convolution of h of t. But instead of, see, it will take a lot of time. So instead of that, we will do the analysis in the frequency domain. So instead of doing the analysis in the time domain, it will take a lot of time. So instead of that, we will try to do the analysis in the frequency domain. That is our basic agenda. The basic agenda of this signal system is to make the things very simple. Within a less amount of time, we need to get the output. So then, for f of t, the Fourier transform is f of omega. For h of t, the Fourier transform is h of omega. And for y of t, the Fourier transform is y of omega. So therefore, y of omega is the multiplication of the two things, f of omega into h of omega. So the multiplication is very, very simple, right? So try to find the Fourier transform of f of t, try to find the Fourier transform of h of t, and do the multiplication of these two Fourier transforms in order to get the output Fourier transform. Then with the help of inverse Fourier transform, we can get the output signal y of t. So this is a very, very simple thing. So instead of doing the conversion of time domain, it will take a lot of time. So instead of that, we can do the multiplication of the frequency domain, and by applying the inverse Fourier transform, we can get the original signal. So this is what I am trying to tell you. So therefore, we can say for f of t, the Fourier transform is f of f of omega, and for h of t, the Fourier transform is h of omega, and if y of t is equal to f of t combination of h of t, then y of omega is equal to f of omega into h of omega. So the conversion time domain, it will become multiplication in the frequency domain. So this point always you have to keep in mind. So conversion time domain, it will become the multiplication in the frequency domain. So this point I have already told you so many number of times, and you have to always keep in your mind. So the conversion the time domain, it will become multiplication in the frequency domain. So the basic agenda of this course is to make things very simple. So therefore, try to do the multiplication in the frequency domain, and just by applying the inverse Fourier transform, you can get the corresponding signal in the time domain. So it makes things very simple. So let me write here. So that you can easily able to understand. So what is the formula I will take? Is if y of t is equal to f of t convolution of h of t, then y of omega. So y of omega is nothing but f of omega into h of omega. So this is what I am trying to tell you. So this point always you have to keep in your mind. Now let's go for the another thing, which is the multiplication property. So what will happen if the two signals are multiplied in time domain? Then what is going to happen in the frequency domain that we are going to see? Vice versa. Previously, the convolution in time domain has become a multiplication in frequency domain. Here, multiplication in time domain means it will become convolution in frequency domain. Vice versa, it will become. So multiplication property. So for f of t, the Fourier transform is f of omega, and for h of t, the Fourier transform is h of omega. So if the output is a multiplication of these two signals, then what is going to happen? Which is f of omega is equal to 1 by 2 pi f of omega convolution of h of omega. So 1 by 2 pi, we have to take extra thing. So therefore, multiplication in time domain will become convolution in the frequency domain. So for f of t, the Fourier transform is f of omega, and for h of t, the Fourier transform is h of omega. Then y of t is equal to f of t into h of t. It is nothing but y of omega is equal to 1 by 2 pi f of omega convolution of h of omega. So always remember, which is the convolution in time domain will lead to multiplication in frequency domain, and multiplication in time domain, it will lead to convolution in frequency domain. So this point always you have to keep in your mind. So this is what I am trying to tell you from all this time. So whatever the convolution in time domain, it will lead to multiplication in frequency domain, and the multiplication in time domain, it will give you convolution in frequency domain. So this is what I am trying to tell you from all this time. So finally remember, convolution in time domain, it will lead to multiplication in frequency domain, and the multiplication in time domain, it will lead to convolution in frequency domain. So let me write the formula here. So that you can easily able to understand. So if y of t is equal to f of t into h of t, then y of omega is equal to 1 by 2 pi into f of omega combination of h of omega. So these things always you have to keep in your mind. So now, like this, always you have to keep in your mind. The next property is the integration property. So integration property that we are going to discuss. Suppose the input is integrated, and what is the output in the frequency domain, we need to figure out. See, for f of t, the Fourier transform is f of omega. If y of t is the integration of the f of t, y of t is integration from t is equal to minus m to t f of t dt. Then what is the output? What is the Fourier transform? We need to figure out. So we can write like this: f of t convolution of u of t. You can write it. So f of t convolution of u of t is nothing but simply integration from t is equal to minus m t f of t dt. So therefore we can say that integration from t is equal to minus m t to t f of t dt. So therefore this is the y of t. So how we can get? So basically we can say y of t is a f of t convolution of u of t. So the convolution time domain, it will become multiplication frequency domain. So y of omega is equal to f of omega into u of omega. So f of omega, u of omega means for the unit step signal, what is the Fourier transform? Just now we have studied. What is the, for u of t, what is the Fourier transform? For u of t, just now we discussed, right? For u of t, what is the Fourier transform? Is pi delta of omega plus 1 by j omega. Pi delta of omega plus 1 by j omega. So this is the Fourier transform for the unit step signal. Then multiply f of omega inside, then we are going to get f of omega by, here f of omega into 1 by j omega is f of omega by j omega plus take f of omega inside. So pi into, here basically we are multiplying f of omega with delta of omega. If delta of omega is an impulse signal at omega is equal to 0, then if you are multiplying with f of omega, its f of omega is nothing but it will become f of 0 at omega is equal to 0. What is the value that we need to figure out? So pi into f of 0 into delta of omega, pi into f of 0 into delta of omega, because this is the impulse signal. So whenever you multiply f of omega and delta of omega, it will take only the impulse at a corresponding omega is equal to 0. So therefore we are going to get pi into f of 0 into delta of omega. So this is the thing that we are going to get here. So this point always you have to keep in your mind. So f of t, is nothing but for f of t the Fourier transform is f of omega is the integration of the input, which is integration from t is equal to minus into t f of t dt. For this, what is the Fourier transform I want to figure out? It is nothing but y of t I am going to assume. So this we can write like f of t convolution of u of t we can write. So the convolution time domain it will leads to convolution time domain it will leads to multiplication of frequency domain. So y of omega is equal to f of omega into u of omega. So f of omega, and you know the Fourier transform of unit step signal just now we have studied, which is pi into delta of omega plus 1 by j omega. So I have taken omega f of omega inside. We are going to get f of omega by j omega plus pi into f of 0 into delta of omega. So this is the expression that we are going to get. So let me write the final output. So listen carefully. For f of t, the Fourier transform is f of omega. Then for integration of t is equal to minus t to t f of d dt, f of t dt. Basically it should be tau. If it be tau, specifically speed, it should be tau. So let me write here so that we can easily able to understand. So let me write here. So let me specifically what means it is not t, it is actually tau. So let me write here. Integration from tau is equal to minus t to t. Tau is equal to t f of tau dt. So basically this is integration of the input, right? Then for this one, what is the thing that we are going to get finally, which is f of omega by j omega plus pi into capital F of 0 into delta of omega. So this is what we are going to get. So for f of t, the Fourier transform is f of omega. Integration of tau is equal to minus into t of tau dt is nothing but this Fourier transform is f of omega by j omega plus pi into f of 0 into delta of omega. So this is what I am trying to tell you. Now, the special case that we are going to study. So now, as I already told you, special case, what is a special case here, which is, so basically, f of omega, you know, right? F of omega. What is f of omega? So f of omega, just now we have said that integration of t is equal to minus t to plus infinity f of t into e to the power of minus j omega t into dt. Just now we discussed. So now, what I am going to do, in place of omega, I will substitute 0. In place of omega, I will substitute 0. Then what I am going to get? F of 0 is equal to integration of t is equal to minus plus t f of t dt. Because in place of omega, I will substitute 0. Suppose if this value is equal to 0, then what is going to happen? Suppose if this value is equal to 0, then what is going to happen? Let me see here. So for this case, y is equal to integration from minus f to t f of t dt is nothing but f of omega by j omega. So this f of 0 is nothing but its value is 0. In special case, we have studied that this value is equal to 0. So therefore, if this value is equal to 0, so overall value is equal to 0, it will become only this value we are going to get. So therefore, what I am trying to tell you, suppose if at omega is equal to 0, if this value we are going to get, it is equal to 0. Suppose if this value is 0, if this value is 0, then we are going to get only this thing, right? So therefore, what is the special case here? Let f of 0 is equal to 0. Suppose if let f of 0 is equal to 0, then what is the meaning of this one? Then the answer, what is the answer? We are going to get f of omega by j omega, you are going to get. If f of 0 is equal to 0 means what is the meaning of that term? It indicates that the area of the f of t figure is equal to 0. Yes, the area under the f of t is nothing but it is equal to 0. So the area under the f of t, if it is 0, then only f of 0 is equal to 0 and the Fourier transform of omega is equal to 0. Its value is 0. Then if you simplify in the previous expression, we are going to get only f of omega by j omega we are going to get. and this value is equal to 0. So this is a special case we have studied. So these are the different properties that you always have to keep in your mind. So finally, repeat all these formulas so that you can easily able to understand. So these are the different Fourier transform properties. Fourier transform properties that you always have to keep in your mind. So for f of, this is a time shifting property. For f of t, if the Fourier transform is f of omega, then for f of t plus or minus t naught, the Fourier transform is e to the power of plus or minus j omega t naught f of omega. This you can remember with the help of the Laplace transform. So if you remember the Laplace transform, same thing here also, same thing. Just replace s by j omega. Then we are going to get this value. Suppose if you take plus or minus separately and if you add, we are going to get this value. If you do the subtraction, then we are going to get this value, right? So these things always you have to keep in your mind. So now let's go for the time scaling property. Time scaling property we are going to study. So for f of t, the Fourier transform is f of omega. And for f of a t, the Fourier transform is 1 by mod a. F of omega by a. A can be positive or a can be negative. A can be greater than 1 or a can be lesser than 1. If a is greater than 1 means it is compressing the signal. If a is less than 1 means it is expanding the signal. So multiply by mod and both sides and we are going to get mod a into f of a t is nothing but f of omega by a. So this is a different way of writing. So now the next thing is here frequency shifting. Frequency shifting property, which is for f of t, the Fourier transform is f of omega. So here basically let me write in the second format so that you can easily able to understand. E to the power of plus or minus j omega naught t, the f of t has a frequency domain f of omega minus plus omega naught. So this is the thing that you have to keep in mind. So this are written in the standard format so that we can easily able to understand. So e to the power of plus or minus j omega naught t has a Fourier transform f of omega minus plus omega naught. Here this plus means it is a minus, it is a minus means here plus. So this is what always you have to keep in your mind. So therefore frequency shifting, we are either frequency delaying or frequency advancing. So e to the power of plus or minus j omega naught t f of t as a Fourier transform f of omega minus plus omega naught. Here plus means here minus, here minus means here plus. So these things always you have to keep in your mind. So e to the power of plus or minus j omega naught t f of t as a Fourier transform, which is f of omega minus plus omega naught. Then here suppose f of t into cos omega naught t. I have already told you cos omega naught t, you can write e to the power of I omega naught t plus e to the power of minus I omega naught t by 2 and multiply these two signals and then apply this property, Fourier transform property. We are going to get 1 by 2 f of omega minus omega naught plus f of omega plus omega naught. Similarly f of t into sin omega naught t. Sin omega naught t you can write e to the power of I omega naught t minus e to the power of minus I omega naught t by 2j. We multiply and if you apply the Fourier transform with the help of this property, we are going to get 1 by 2j f of omega minus omega naught minus f of omega plus omega naught. So if you remember this one, v plus plus by minus and here keeping extra j downward. Then I have already told you, suppose if you want to find area under the Fourier transform signal, if you want to find the area under the Fourier transform signal, which is integration of omega is equal to minus to plus infinity f of omega d omega. If you want to find the area under the signal f of omega, which is equal to 2 pi into f of 0. So at t is equal to 0, in that time domain signal f of t, at t is equal to 0, find its value and multiply by 2 pi. Then we are going to get the area under the f of omega. Then we can get the area under the f of omega. So this expression we have got from this one. So these things always you have to keep in mind. So let me write this vectors also. So f of omega is nothing but integration of t is equal to minus infinity to plus infinity f of t into e to the power of minus j omega t dt. So then what is that? Small f of t is equal to 1 by 2 pi integration of omega is equal to minus infinity to plus infinity capital F of omega, here minus means here plus j omega t omega. So this is what we have to keep in your mind. So if you want that, here in place of this expression, substitute t is equal to 0. If you substitute t is equal to 0 and here multiply by 2 times both sides, then we are going to get this thing. So this is the area under the Fourier transform f of omega signal. And if by using the Parseval's theorem is going to find the energy in the signal f of t and f of omega. For the corresponding f of t, we are going to get the Fourier transform f of t. The energy is same in both the f of t as well as the f of omega. What is the expression? E is equal to integration of t is equal to minus infinity plus infinity mod of f of t whole square dt. This is the time domain. If you want to express the frequency domain, which is 1 by 2 pi integration of omega is equal to minus infinity plus infinity mod of f of omega whole square d omega. Suppose, basically, I already told you the macro spectrum is basically it is a even spectrum. So if it is even spectrum, we can simplify this one. So 1 by 2 pi into 2 times of integration of omega is equal to 0 to plus infinity mod of f of omega whole square d omega. So to the cancels, we are going to get 1 by pi integration of omega is equal to 0 to plus infinity mod of f of omega whole square d omega. So now here this is in terms of omega. Suppose if we want to write in terms of frequency f, so omega is equal to 2 pi f, so 2 pi cancels, so d omega is nothing but df, so therefore we simplify, so omega is equal to 2 pi f, so d omega is equal to 2 pi df, so replace d omega by 2 pi df, so 2 pi cancels, and now omega is equal to minus infinity, f is equal to minus infinity, if omega is equal to plus infinity means f is equal to plus infinity, so that it will become integration of f is equal to minus infinity plus infinity mod of f whole square df. So I already told you the macro spectrum is a even spectrum, so because of that it will become 2 times of integration of f is equal to 0 to f is equal to infinity mod of f whole square df. These are the different ways of expression. So suppose the multiplication of the input signal f of t, then what is going to happen in the frequency domain that we are going to study. So for f of t, the Fourier transform is f of omega. For t into f of t, the Fourier transform is j into d f of omega by d omega. So for f of t, the Fourier transform is f of omega. For t into f of t, the Fourier transform is j into d into f of omega by d omega. Similarly, the dual's property that we are going to study. So for f of t, the Fourier transform is f of omega or f of f. Then what is the capital F of t? So for capital F of t, what is the Fourier transform? 2 pi into f of minus omega. So basically, suppose for a given time domain signal, we got the frequency domain signal. So I want to have a same picture in the time domain for the frequency. Then I want to get the corresponding expression of the frequency. I want to get the expression in the time domain. Frequency domain I want to figure out. It's 2 pi into f of minus small omega. So therefore, here listen carefully. So like this, this is like this, and this is like this. So f of t as a Fourier transform f of omega. So for capital F of t, the Fourier transform is 2 pi into f of minus omega. Means replace 3 pi minus omega and multiply by 2 pi. This is in terms of omega. But if you want to get in terms of f, means here it is a capital F of f and here capital F of small f of minus f. So here capital F of f and here small f of minus f here. That's it. This replace 3 by minus f here. That's it. So here listen carefully. This is in terms of capital here omega and here f. You can write anything. So therefore, for capital F of f and here small f of minus f. This replace 3 by minus f here. That's it. So these are the different expressions in terms of frequency. This is in terms of omega. Suppose if you want to find the area under the f of t signal. So if you want to find the area under the f of t signal, then use this formula. So if you want to find the area under the f of t signal, means a plus omega is equal to 0. Over a plus omega is equal to 0. This value will become 1. So it will become f of 0. And the remaining thing is integration from t is equal to minus to plus infinity f of t dt. So this is the area under the f of t is nothing but capital F of 0. So at omega is equal to 0, try to find the value of the Fourier transform and substitute here. That's it. We are going to get the area under the f of t signal. So integration of t is equal to minus infinity plus infinity f of dt is equal to f of 0. And we are going to discuss the combination property. So I already told you that combination in time domain, it leads to multiplication of frequency domain. So if y of t is equal to f of the combination of h of t, then y of omega is equal to f of omega into h of omega. Similarly, I want to tell you the multiplication property is the vice versa is also true, which is the multiplication time domain, it will lead to combination frequency domain. If y of t is equal to f of t into h of t, then y of omega is equal to 1 by 2 pi into the f of omega combination of h of omega. This one you have to keep in your mind. So finally, the integration property that we are going to study. Suppose if f of t has a Fourier transform f of omega, then the integration of the signal, we want to find the Fourier transform, which is integration of y is equal to minus infinity to t f of 2 b2. So means the integration of the previous signal, I want to find the Fourier transform, which is f of omega by j omega plus pi into capital F of 0 into delta of omega. So this is the expression that we are going to get. Suppose I am going to assume capital F of 0 is equal to 0. What is the meaning of this one? It indicates that if this value is equal to 0 means the area under the f of t is equal to 0. Then what is going to happen? If this is 0 means this value we are going to this capital F of omega by j omega. So this is the value we are going to get only when f of 0 is equal to 0. If it is not equal to 0 means this is the overall expression. So all these formulas always you have to keep in your mind. So these are the Fourier transform properties always you have to keep in your mind.